Okay, so everybody, we are here for the second week of the Grace Code School. So this morning it will be a bit special because, of course, Joel is not able to attend the school this morning because once you have an appointment with a hospital, of course, you don't want to postpone it. So that's life. It's happened, but we managed to get some videos recorded just for this school to make sure that everything will be quite straightforward to follow. So normally we'll play the first part of the lecture just before the break, and then we will continue with the second part, and then we will do some magics with some GPU this afternoon, but this will be for this afternoon. So, Joel, it's up to you, virtually. And yeah, Joel will answer all the questions live on Discord, of course, if you have some question. And we can also answer them if there is a lot of questions, of course. So don't worry, I will try to not pause the video to be sure that to be on time, but normally everything should be answered on time. So Joel, it's up to you.
Hello everybody, welcome to this course about the expressive vector engine, the Eve library. I'm Joel Falcou. I wish I would have been able to be with you in person, but unexpected health issues stranded me in, so all my my excuses for not being there. A small bit of logistics about these pre-recorded courses, so everything can be, cool for everybody. We are going to have a look at a bunch of things, a bunch of codes. Some of them are in your Docker container concerning Eve, some are not. I encourage you to try and manipulate the library on your own. After a while, we are going to see how it works, so we can compile it and so on. I will be available on the Discord server starting this afternoon and all week long. So if you want to snatch me and ask me about stuff, issues, or whatever about Eve, don't hesitate. I will try to be helpful on this matter despite the circumstances. A bunch of links are put into the PDF for accessing some kind of runtime of the examples. They are hosted by on the CodeRecon's learning platforms. So you can have a look at them, not necessarily modify them unless you already have an account on the platform, but it should be okay for transporting the code and the results. Okay. I will stay over there during the video so you can see me. Some people like that. And again, if you have any question, I will be able to answer them after the after this video starting this afternoon. Okay, so now let's dive into the actual matter. We are going to speak about, again, vectorization, but this time, instead of letting the compiler try to do something, instead of relying on other library, or worse, instead of trying to write SIMD intrinsic by hand, we are going to explore another venue, which is manipulating and writing SIMD-enabled code using some high-level C++ library. So let's start by maybe getting a refresher because you heard about it, you get some courses already on that, but it's cool to go back to the very beginning about what, how, and why we want to do SIMD programming. And first, what is actually SIMD programming, okay? So let's start by something else. Let's start by speaking about SISD. So SIMD, SCISD, and you probably also heard about MIMD are all nomenclatures from the Fin classification that basically dispatch parallel system into different categories based on the number of instruction stream and data stream the machine is able to process. An SISD machine, it's a single instruction, single data machine. Okay, so it basically runs one stream of instruction over one stream of data. Stuff happens somewhere in the processor or whatever, and you get one result. And every so much cycle, a new instruction goes in with data or a bunch of data. Something is computed, and we got a result. Basically, whenever you use a single core of your processor without doing anything fancy, you are basically running on a SISD machine. It's a bit more complicated than that, and I see people over there in the back. It's a bit more complicated than that because sometimes a modern CPU can take the liberty of running some instruction out of order to split an instruction into simpler one or other tricks like that, being super scalar and whatnot. But in the end, we can simplify all of that by having this step block, instruction stream, data stream, and we get a result stream. And at some point, somebody came up and said, okay, that's a bit wasteful because I have a bunch of transistors I don't use. Okay, it happens sometimes. So maybe I can have registers which are larger than usual. And instead of fitting inside more bits for an integer or more precision for a floating point value, what about we put multiple value inside those? And that's what SIMD is actually. We still have a single instruction stream, okay. But now the data stream is actually multiple value per instruction. They are usually stored into what we call wide registers. Those registers contain value in different lanes. And the idea is that those instructions operating on those data produce the same amount of results with a cost in cycle, which is basically roughly the same as a SISD machine. And so what we expect when everything will be okay, what we expect is to get a speed up coming from the fact that the registers are wider than regular ones. If I consume and produce 4 integer results per cycle whenever I do, I don't know, like a complement, a big complement, instead of processing 1 integer per cycle, I expect to go 4 times faster. And again, I will put some emphasis on that because I know it's complicated and there was a lot of questions about that last week. This is not multiprocessing. This is not multi-threading, okay? This is inside a single core of your processor. So SIMD is basically a source of performances that come from the fact that in a single core of your processor, multiple operations can be applied on multiple data at the same time every cycle. And this is where we want to grab some additional speed up. And as it's inside one core, it's composable with the fact that you are going to run OpenMP on top of that, and you are going to run MPI on top of that. It's an additional leverage of performance in the end. It's a very low level one, and we have to be careful about what we do with that. The performance are actually tied to a lot of other factors we are going to discuss, but if we put that into perspective, it's basically just using some subtop registers that already live in your processor, and that most of the time, unless auto-vectorizer come in, nobody is actually using. Okay, fine. But what are those registers actually? As we said, SIMD registers are organized into what we call lanes. Okay, a lane is basically a single value inside the YOL register. But whenever we apply an operation on a SIMD register, the same operation is in parallel applied to each lane, each value inside the register. Depending on the architecture, x86, ARM, PowerPC, and even in a single architecture, depending on the flavor of SIMD extension you want to use, you have more or less lanes per SIMD register, and you have more or less the same family of type inside. Some architecture doesn't support double, some doesn't support 64-bit integers. Well, nowadays, they all basically support everything, but it's not a guarantee. And so if we take the example of the x86 SSC extension that use 128 bits registers, we see that we can look at them as either a pair of 64 bits element, double or long, a quadruplet of float or 32 bits integer, a pack of 8 16 bits integer, 8 short or 8 integer short, and 16 8 bits value. And we see that quickly 8, 16, that's basically one order of magnitude in terms of performance. If I was able to get a X10 on processing 16 char each time I use those kind of register, it's a massive win. I jump one level of magnitude. And that's only the 128 bits version. We are going to see that we are 256, 512, or even 1024 bits register. And each time we double the size of the register, we have more and more value per register of the same type. One thing we need to be careful about that at some point, we cannot just continue and make those registers grow, because at some point, if your register is bigger than your cache line, you will have some issues. But CPU vendors sort of know about that. So yeah, so we have these multiple things. One very easy way to get around that is to see a CD register as a small hardware-based statically sized array. That's a very crude simplification, but it's basically this. Okay. So now, what happens when I try to make some operation on that? We can visualize this way. If you do an addition between two registers containing 8 value, let's say it's 8 shorts, what happens is in a single pass, we are going to have those 8 results computed directly into the results. That's where the performance speedup lies. The fact that we can do all of that basically in the same time, the same space, that we can do a single one. So now, we said that we had a bunch of different architectures and extension. What are we actually talking about? We basically are thinking of this. The first CMD extension set came from the the late 90s, early 2000s, with SSC and VMX that we also known as Altivec. And as we see, as time goes, the number and the variety of CMD extension just keep growing. Okay, so we have all the SSC variant that are all the x86 Intel 128 bits register extension that got replaced by AVX AVX2 in the 2010s that are 256 bits instructions. And then later on in 2016 and above, the advent of AVX 512, and the name says it all, it's 512 bits registers. But in the meantime, while Intel was running a mock like that, PowerPC with VMX and then QPX and VSX tried to improve. PowerPC is now a bit different, but it was also a very good system. The underdog was ARM with Neon that got updated to ASIMD to support 64 bits values, still in a 128-bit register. And it came back in the 2020s with SVE and SVE2, which is a bit different. It's a flexible size between 128 and 1024 bits registers. And at the same time, we got new things like the SIMD for WASM. Okay, so you can have SIMD in your browser now. And RISC-V, which is a big new thing right now that is very similar to SVE and AVX 512. Okay, but what about my machine? How do I know? How do I know that I have this or that thing available? To do that, we have different way of guessing or getting the information about what your machine is actually getting. On Linux, you can either use LSCPU if you have it installed, or you can install it's a classical package, or you can look inside proc CPU info. We are going to get a look at that. If you're on macOS, you can go through the bash CC-FR command or the equivalent C POSIX functions. And on Windows, if you are on PowerShell, you can install sysinternals and have access to core info. So let's have a look at what happened on Linux there. So I am on some, I am on some WSL machine, but that doesn't change. I can actually run LSCPU there. So we got a bunch of information, and what we are looking for stands in the flags part, okay, where we can see that I have SSC, I have SSC2, a bunch of other SSC whatever. Where are you? AVX, AVX2, F16C, which is also a similar instruction set dedicated to floating point of 16 bits. And on this machine, that's all. I don't have anything else. We could actually go to some ABX512 machine. It happens to be there. And if I do it this way, LSCPU, you can see that indeed, well, you know what? It's a lot of things. So let's grab a bit. Okay, what flavor of ABX512 do we have? Yeah, a bunch. Okay, we are going to see how it works. But I have ABX512. I got obviously all the other, and so on and so forth. If I do proc CPU M4, what do I get? I get basically the same thing. It's the internal elements of what we got with CPU, LSCPU. So we can have those information. If you want to have those information at runtime inside your program, you can use the CPU ID or some variations thereof. It's a low-level instructions. It's a bit complicated to use. We are going to see later that we have a wrapper for that. So you can actually get access to that at runtime. Okay. So there is a lot of different instruction sets. Okay, that's the first information. But the question then is why I want to dabble with that, and how do I exploit this? Okay, so maybe you want to go fast. So your first thought could be I'm going to run on GPUs, except some code doesn't fit GPU model of programming. Okay, or you cannot have a GPU for that, depending on your energy budget or your budget alone. And SIMD instruction sets are basically everywhere. If you have a processor that has no SIMD instruction set, it's a machine from before the 2000s. So that's time to, ask your hierarchy for getting a new machine. Okay, you see what I mean. So it's already there. So why not using this X4, X8, X16 speed up? Why should I consume more cores? Why should I jump over a GPU with all the problems the GPU causes actually? So you see that you can abuse and use a SIMD instruction set by trying to auto-vectorize manually. You can use OpenMP4 pragmas. You have special compiler like ISPC that can do the job for you. There is some libraries that wrap some standard looking algorithm. You have the STD execution that do some. HPX also do some. Or you can use specialized tools. You do image processing, maybe have a look at ALID that provide you a domain-specific language that take care of this vectorization, among other things. You are dealing with JSON file and you want to go faster, maybe have a look at SIMD JSON or some other library like that. And sometimes you won't find what you need and you are going to write some SIMD manually. And that's the point where normally I should play some dramatic music, okay? So imagine, okay? So yeah, doing manual SIMD is something that is both alluring and terrible at the same time. So SIMD programming use intrinsics, which are basically small magical functions that the compiler recognize, okay, and turn into the actual low-level assembly bits that do the manipulation of the how to say that, of the SIMD registers. It's very direct. It basically generates a single or a couple of specific machine instructions. But to use them, you are going to use specific data types that are usually ugly types, let's say it this way, that doesn't behave like you want, that needs to be wrapped somehow, and you have to remember what you do with them. So intrinsic, we provide the operations, okay, on those intrinsics. As we are going to see, it's not that easy, actually. Okay. Sometimes you have most of the time, functions that are dedicated to loading data and storing data between the main memory and CMD register. One very specific behavior that we have whenever you want to write your own CMD operation, CMD algorithm, is the fact that most, if not all, memory movement back and forth from the memory to the register has to be explicit. And we are going to see that, yeah, it's a mouthful sometimes, let's say it this way. But in practice, well, what do we get from that? Well, you get maximum performance, and people like that. You are writing exactly what the CPU should be doing. You are going to fully utilize whatever the CPU is giving you in terms of registers and complex operation. You are going to go fast. Under the pretense that you are going to understand what you are going to write. Yeah, you can manage the very minute details of your implementation, where and when the memory is accessed, how many numerical tricks you can apply that will help you go faster and whatnot. At the cost of a limited portability, because whenever we are going to see that right now, whenever you use one of the specific, how to say that, how to say that, on the specific size and whatnot, okay? You are going to have to think a lot about a slew of complex algorithm and structure of your code, okay? Next to that, you are also going to know exactly what the architectures you are targeting is able to do at this level. Because as we say, we don't have every operation on every instruction set. And sometimes you are going to do, well, you have to be creative. And to understand this, let's have a look at the actual subset of intrinsics we can get. You know what? Let's just do something simple. Let's go have a look at x86 intrinsic list for CMD programming. Okay, let's zoom a bit. Okay, so this is the Intel Intrinsic Guide webpage. Okay, that basically lists, as the name implies, all the intrinsics for all and every CMD instruction set that x86 is providing. And as you can see, with this very, very pragmatic measure of, well, the size of the slider, yeah, it's massive. Okay, it's I don't know how many actually. So let's focus. Let's just focusing on the 128 bits family, right? Yeah, it's still a lot. Still a lot. Multiple issues, as we said. We have those funky types. __ M128i, M64, the 128, 28D, and whatnot. Okay. So basically, well, it's not that complicated. 128i, it's an integer register. 128, it's a single precision floating point register. With a D, it's a double precision. Fine. And then you have the naming scheme of the function. Some are okay. I mean, I kind of guess what this is doing. Probably a vectorized version of 16 bits absolute value, addition, and whatnot. Add sum, what? I'm supposed to do the same thing on both. What is that? Line R, AVG, blend, my favorite BSRLLI, okay? And it starts to be a bit complicated. Okay, some have ugly things. But let's see. Do I have, like, for example, how many multiplication do I have in the SSC thing? Multiplication. Yeah, multiple. So we have some things for the 32 bits, sign or unsigned, for the floating point. And that's all. I don't have anything for less than that. Oh, well, you know what? Maybe I can have a look at division. Oh, that only exists for floating point numbers. Or maybe I have, like, I don't know. Let's have a look at absolute values that only exist for some integer size. So we have alls. And whenever we go up a family, you see that they get completed. So that is now the AVX intrinsics, okay, on 256 bits. Now the neighbors register change, this also change, and if I keep doing this, AVX 512 also, and it has like a lot of them, okay? I just want to make an absolute value why I am supposed to look at this massive list. I don't know what to use, and some of them are actually not what you want. And sometimes you have, you know, I mean, you can load data. Let's focus on AVX 512, for example. You can load data somehow. Oh yeah, maybe I can add data somehow. Okay, even that starts to be very complicated. And sometimes you have a funky thing. Where are you? Oh, where are you? No, it's not. Oh, field. Oh, okay. Is it not there? Oh, come on. Yeah, G something. 512G. Where are you? Oh, come on. Okay, there is some fancy things going on. Okay. Yeah, a bunch of things. You can do a lot. Okay, it's not there. Or maybe it's not there. Let's try to. Yeah. You have wonderful things like this. Okay, which is obviously, as the name implies, the computation of an affine transformation is a Galois field of 2 to the 8th, which is defined as a x times x plus b operations, where you have an 8-bit matrix and an 8-bit vector that gets stored into an 8-bit packed results. If you didn't understand a word of what I just said, don't worry, neither do I. Okay? That's one of those very obscure functions that are just there, while in the same time we don't have the basics like absolute value for floating point numbers. So we have this very wide set of operations, and sometimes we lack the basics. Oh yeah, but maybe that's Intel, you know. I mean, you know how they are. Okay, so let's go to the ARM intrinsic list. Maybe it's better. Yeah. Oh, you can have a look at the 4,344 different neon functions. Let's say I'm only interested in the floating point computation. That's still 834 functions. Okay, let's say I'm only interested in 32-bit floating point in the modern system. Yeah, 300 and something. So we have the basic, we have add, and we have mul, and we have mulex. Okay, and mulex lane, and mulex lane Q. Okay, and you see that we are back into, you know, the international contest of how can I name my function so people have no clue what the heck they are doing. And I am supposed to know that, okay, to look at this kind of documentation where, I mean, I don't even know what I'm looking at. And I'm forced to do that? Yes. Yes, you are. Been there, done that. 0 over 10, don't recommend, okay? You want to do a times b plus c, right? With 32 bits integer? Well, in SYCL, good luck. You have no way to do that. That fit into a slide. You have to combine arbitrary whatever in SYCL4. And if you go on PowerPC, you have that for floating point number. So you have to convert everything into a floating point number, do the computation, go back to the integer. ARM, well, you have it. You have a vmul E32. Done. Other extension, you don't know. And that's just a times b plus c. It's not even a big thing. Okay, right? As soon as you go upper than that, you're basically on your own trying to reconstruct basic operations. You want to do trigonometry? Well, sad to be you, there is none. There is very few transcendental functions. And when they exist, sometimes they have very poor precisions. And so, for having been through that back in the day, I mean, 80% of what you should know about CMD programming by hand is to try to find a way to know the tricks that people from the 2000s discover by accident, transmit by oral tradition, you know, including, visiting them on the top of some mountain during winter or whatnot. So you know what exact incantation you should put into this so that it makes sense to the CPU. And I speak about a lot of ugly tricks. We are going to see a bunch of them at some point, and you don't want to know about that. You're here to do some physics computation. You are here to do some statistics, and so on and so forth. So the question is, why, are those things not so complicated? Well, because the emphasis has been put onto whatever the hardware is supposed to do, and the high level, the user-facing interface is often an afterthought. It has to go to some intrinsics, it has to generate the proper compile time, whatever. But how? Well, I don't know. Somehow. Okay. So this is a bit infuriating, okay, because I just want to compute some stuff. Okay. And I'm forced to deal with that, and sometimes in documentation that even if it wasn't there, we don't know if we could see the difference. So it's verbose, it's difficult, it's non-portable. God forbid you have to support two different extension sets, even on the same architectures. So often people just pick a choice, pick an architecture, and they say, oh yeah, we optimize for that. The rest, I don't know. So sometimes what you want to do is to use wrapper libraries that are more user-friendly because they do all these preemptive tasks of gathering the information about whatever kind of tricks you need to put into your code so it works. And actually expose that into an API that makes some sense. Sort of. There is a bunch. I'm just focusing on some that you maybe know already, or they are, whenever I make a paper, I have to seed them, so they are somehow important. iWill, which is developed by Google, it's a wrapping library that use of macro and reentrant code generation. It works. As usual, caveat, it's a Google library. It exists right now. Will it exist in a month, in a year? I don't know. You have SymDE, that is just a compatibility layer that lets you write any intrinsic from any extension into any others, and the library just polyfill whatever you miss. So if you have a code using SSE2 that uses SSE2 intrinsic, you can port it to ARM, use SymDE, and SymDE will replace the intrinsics, the SSE2 intrinsics by the corresponding ARM intrinsics, and you will see nothing. Performance are not guaranteed because sometimes you don't have a one-to-one, correspondence, but it tries to make it work. And sometimes it's a good thing because you can just try and get something working. XMD, it's C++14 libraries that do classical wrapping, okay, that we are going to see. And starting from a few months now, we have std-cmd in the C++26 standard. How to say that? It exists. That's one of its main selling point. It's still not very well supported by most of the compilers. Some, I'm not even sure if we are going to have an implementation anytime. And it's sometimes very crude in terms of interface, but that's my personal opinion, because I'm clearly biased, because I am one of the authors of Eve, which is also a wrapper library for that. It's a re-implementation of something that was a bit long ago called BoostSymD, and that is basically one of the great ancestors of all of that. Okay, so we just get a new facelift. So yeah, so what do we propose into this? So Eve is based on C++20, and it proposes a library of core types that wraps all what you need to have to deal with SymD intrinsics. So you are going to have a proper API over those SymD registers. That makes sense. You have a bunch of algorithms that let you build more complex structures, and we have over 250 numerical functions that we are going to see a bit later. We work on x86, we work on ARM, on 64-bit ARM, PowerPC, even if it's less tested right now because we don't have a machine, but it worked. We have ongoing work for WASM and RISC-V also. It's both licensed, so it's rather, how to say that, permissive. Okay. It's also, and I want to put some emphasis on that, it's a long team effort from 2016 now, 2018. So big shout out to all those people. So Jean-Thierry, which is one of the first collaborators we had, Dennis also, which is which was the mastermind behind the rework of the algorithm system. Alexis Owen, Adrien Enro, Pierre Estery, some other of my former PhD students that build or collaborated into implementing parts of this library. So what can we do? Well, you can find us on GitHub. Let's do that. Okay, so we should be... Oh, where are you? Okay, so we are somewhere on GitHub. Yeah, gfalcool/eve. Okay, click on the star. We like that. Make forks and whatever. So you can just clone ourselves from there, and you get basically whatever you need. We have a somehow extensive test system, just so you know that we care about the quality of whatever we are going to provide. We have like some documentation tests, randomized precision tests, and I don't know, many, architecture set we do with something over, how much do we have? Yeah, almost 800 tests, just so we have everything going on. Okay, so we do things. Oh, okay. I make a stupid things. Okay, I'm a professional, but that's what you get by not looking at what you do. Let's go back there. Okay. So as I said, we are on GitHub. You can play with us on different places, and we have some documentation that has a bunch of references. You get a bunch of tutorials if you want, different things. And we have some reference documentation at the user level, at the developer level, and whatnot. So let's have a look at what kind of math do we do. Well, all the basics. We got some complicated math. Okay. Disclaimer, there is function, I don't even know what they do. They are Jean-Thierry Lapreste work, and it does the math. So it works. So we got some special function and whatnot. Okay, you can see that we are some kind of serious library because we have LaTeX rendering into our documentation. But jokes aside, yeah, we have a bunch of those. We have just ending for numerical constants. We got a bunch of triggers and whatnot. And let's have a look, for example, at where are you, cosinus? Yeah, so we have some documentation. We have a bunch of information there. And usually we have an example that you can copy paste or you can run online. And normally, didn't select the proper one, you get some kind of real-time output of whatever test you have there. Okay, so we try to have a welcoming environment at this level, in the sense that we want people to understand what's going on and whatnot. So yeah, this is it. So yeah, so you can find us quite easily normally. In the if you use a container, you have if reinstall with a bunch of compiler we like to have, so you can play around with it without thinking about it. Okay, so fine, we do all of that. How does it look? How does it help? Okay, that's the big questions, and where can we go from there? So let's have a look. Let's have a look at how we wrap the things. So the core type inside Eve is what we call wide. Wide is a type that abstracts away a single register by taking a type and a number of lanes that are optional and turns that into the best single register we can have, okay, to do operation on that. And we have a compile time system that let us isolate those variations so you cannot mix up bad binaries one with another. Next to that, we have an API on top of this, where we have access to the basic operation as operators and also as as functions. So all the basic arithmetics, all the bitwise operations, the basic math like square root, inverse, stuff like that. We have a fully vectorized CMath implementation, so you can use vectorized cost, x, log, and whatever. We have a substantive set, so fully vectorized special function, Bessel function, combinatorials, okay. Different vectorized polynomials evaluation scheme, some operation inside the register. We are going to have a look at that a bit later, and so on and so forth. So, let's have a look at what we can do with that. And in fact, let's start by having a look at the basic CPP file you have in the container. So let's jump into it. So let's maybe zoom a bit. We want to zoom at this point. So this is a very basic Eve files. We are going to dive into more of those, but this is one of the basic things that you can do and check that it actually works, which is actually important. You have access to the main library without doing anything using the eve/eve.hpp include files. We have others, we are going to see a lot, but this is the basic one. So what do we do there? Let's play around. We have defined a wide of float. A wide of float is a variable that will represent, for whatever machine you have, a potential assembly register able to contain the most meaningful amount of floating point values inside it. Maybe if you are compiling for SSC something, we are going to have a register of 4. If you are on a 256 bits, you are going to have 8 floats, and so on and so forth. We are, as we see there, we are initializing it with some lambdas. That is basically a generator construction. We are going to see what it does. If provide a bunch of objects that let you also know what you are doing and where you are doing it. So we have this if current API object that you can compare to some constant that defines architectures. And when you print it, you know for what kind of architectures you just compiled for. Then we can print the content of our wide register directly. We can do some basic operation like an addition, a square root. So let's see how we can compile that. So we support a bunch of compilers. Our preferred one are GCC 14 and above. And Clang how many? Clang 19 and above, if I'm not mistaken. Yeah, 18 and above. So let's start with GCC. So we are going to compile base.cpp. Okay. We are a C++20 library, so we should compile with C++20. We are going to see what happens if we don't. We are doing SIMD, so we are there to get some performances. So bigger of 3 is probably mandatory. We need to, we need to find whatever is, wherever your event session is. If you are running this inside the container, like I am not doing right now, it's pre-installed into a user local info, so you don't have to do anything. But in my case, I work with my development system, so I will need to put some, additional thing like this. But it's not very far. It should be there. Okay. But as I said, a bit more. You don't have to do that because in the container, it's basically there. Okay, so what did I do? I did a mistake. Oh, yeah, because it's basic.cpp, okay. So I decided to not cut that, so you get the basic, I made a demo without looking at what I was doing feelings, okay. So let's start to do that. It compiles, okay. And let's run it. So I just compile with nothing. And by default, if you compile with nothing, you are compiling for SSC 2 and above. Okay, so what do we have there? If I run this. Okay, so let's go around the print. So we are optimizing for what? For x86 SSE2. Okay, so that's the basic 128 bits register systems. I initialize X by filling it with 1 plus I being the index of the current lane that we want to fill. So I should end up with 1, 2, 3, 4, which is exactly what I have. I compute X plus X, which is 2, 4, 6, 8. And I do some square root, and well, it does what it does. 1, square root of 2, square root of 3, square root of 4. Okay. Yeah, so fine. So I know what I do. I get my result. I don't have to think about what kind of architectures I am doing. I have a wide register, which is the best one for what I ask. If compilation model is based on the fact that we know statically at compile time which architecture we are going to optimize for. So now if I want to get better stuff, or maybe I can use SCC4.2. It's a better 128 bits thing. Let's see what's going on. We should not have very much difference, except now I know that I have access to that. This fine-grained support of extensions is made so that we can always find the most optimal, how to say that, the most optimal series of intrinsics to do one task or another. And whenever something does not exist at a given level, we try to emulate them with different techniques that may or may not include doing some preparation works and ending up doing something with lesser instruction set. That's the way we do the thing. So let's see if I jump a bit, because I have AVX and AVX2 there, so I can go on AVX2. I should have now 256 bits per register, so I expect to have like 8 floating point values in my floating point values. And that's what I got. I got larger vectors. And you see how I didn't touch there. I have a wider float, and whatever I compile for, I got the best one. Which is slightly different than what STD-SIMD is doing, where it tries to get to the lowest common denominator. That's one of our biggest differences. Okay, fine. But what can I do from there? Okay, what kind of thing we can do? You can take some time right now if you want to play around with basic.cpp, try other operators, other basic function. Maybe we can have, I don't know, like let's do that, for example. Oh yeah, let's do this. Let's do 1 minus x, and let's do the square root of x. Yeah, we should end up with negative values. So what does square t roots is going to do? Yeah, did I run the correct one? Oh yeah, but I didn't do the correct thing, so it's 1 minus x, obviously. Let's do the complete error fit. So if I use the correct computation, yeah, I got none, because square root of whatever is none. I don't get any asserts. I don't get any exceptions. I don't get any error code. If is meant to go fast, so we make the assumption that you know what you're doing numerical wise. We have things that help you not do a mistake. For example, we are NaN aware most of the time, so we are going to say you that if you get a NaN, you do something wrong. Okay. Sometimes we are going to see that we have options that will make those errors more blatant. Okay. But we are going to think that you know what you're doing. Okay. And we don't babysit you around these edges. Okay. So I see somebody in the back, the Rust guys, they are currently trying to probably want to kill me, but that's the way we wanted to get. We are there to get performances. It's your job to do the precondition checks before you run the big kernel you just optimized. Okay, you see what I mean. Okay, so maybe I can do something simple. Let's just take the absolute value of that and see what's going on, right? It should be better now. And it does, obviously, because we computed the absolute value and whatnot. Okay. Now, we spoke about the size of the wide, and we don't need to specify them. But you can also specify those. Okay. There is a if fixed value that can take a value like that, for example, that can be used to specify how many lanes you want in the register. So, caveat now, I'm doing some kind of, it's important. So, I'm there now. I'm speaking of this. We are at the 20-something June 2026. Soon, but I don't know when yet, but soonish, probably during the summer, we are going to have a massive ABE breaking changes where fixed disappear to be replaced by just the numbers that is handled differently. So whatever you saw right now is from the pre-simplification PR that maybe is going to come up soonish. Okay, so if it doesn't work, if you look at this video later, this is why. And I'm going back up there. So you can do this. But what happens? Well, let's see what's going on. I can still compile with whatever instruction set I want. And I get the correct things. But what happened? If at compile time is able to take this pair of information, the type and the size, and pick the correct one. So if you compile for AVX2, but you want 4 lanes wider float, you end up with a SSE 4.2 register, because that's the best way to represent that. Okay, what if I go very low in size? Does it make sense? Well, it does. At least the compiler is happy with it. Okay, and it works. In this case, what we do is that we still use the smallest SIMD register we can find, and we just ignore a part of it. Okay. But what if I ask for more? For example, twice the size I should have. Well, guess what? It also works. And let's guess. Okay, let's guess what happens there. Okay, so I should have a jingle at this point. What do you think happens? Small, small silence if you can pause the things right now so people can express their opinion. What happens is, whenever you have a bigger one that your hardware is able to support, we are going to basically slice these big things into the biggest chunk we can have. So on AVX2, this thing is actually internally a pair of AVX registers. And Eve know how to handle those aggregation, like we call them, as if they were native registers. Okay, so what's the limit to that? Well, the limits are rather easy. Your lane count must be a power of 2. So if we do that, okay, let's take some space there. So if you do something nonsensical like this, yeah, we got some errors. Okay, we got some errors. Let's pipeless that. So we have a static assert, and then we have like cascading error. But basically, yes, cardinal must be a non-zero power of 2, which 7 is not, clearly. Okay, so we won't let you compile stuff like that. And that's very important to understand that a wide represents a register. It is not some kind of fancy array. It cannot take arbitrary size. And you know what else we do so people doesn't get confused with that? Well, this is not, this is not a valid API neither. We don't have that. Oh, yeah. If I compound the error, it won't work. Let's go back to 8. Let's compile again. Yeah, we don't have that. It's not an array. Sometimes, however, you want to access a one lane of something, and then you have to use the verbose get function. Yes, it is verbose. It is done on purpose, because if you let people manipulate a SIMD register like array, they write bad code. So one philosophy we have in AIM is that if it's not for you to do, we just don't let you do it. Okay. So that's part of how we work. So we saw that we have a bunch of ways to initialize our wide. Let's have a deep look into this. So you can load data from some place in memory. So we load from an array there. You can load from the dot data from a vector, from a span, for whatever. By default, load performs unaligned load, which is the easiest way to do for users. And we have a notion of align pointer, aligned PTR, that you can use if you want to force the alignment of your load. But most of the time, you don't really care. Modern hardware just doesn't give a crap about, alignment and whatnot. Okay. So you can load from memory. You also have a store function that we are going to see a bit later. You can initialize a wide with a constant. Okay, so if you want to put zeros or whatever. By default, if you don't put anything into your while, and I'm sorry for the guy that doesn't like undefined behavior or the one guy over there that do Rust, if you don't initialize a while, we don't put anything inside. You get an initialized variable, and well, you should check that because we are not responsible for the crap you put into your register. We do that so that we can maintain a high level of performance. So we can do that, okay? And you know what? Let's run this actually somewhere. We can play around in an easier way. So we are now running this code over our coding platform at CodeRecons, okay? Okay, maybe we should be using, yeah, it was compiling something here. So let's go back to this. Okay, so yeah. So we are compiling for AVX2. So we load the 8 values there. 0 is full of 0, and 4.5 is full of 4.5. Okay. And as I said, okay, let's see if the compiler is actually making me a liar. Okay. Yeah, thanks Clang. Okay, Clang is probably cleaning up the register or whatnot. Whatever. Yeah, okay. So obviously when I want it to fail, it won't fail. You know how it goes. Okay, fine. We can do that. We did float there. Obviously, we can have other types. Okay, we can have that. Okay, it's probably 0 there. And yeah, it has to be integers. Okay, so we know how to detect those things. Obviously. Okay, now let's do something interesting. What kind of code are we generating when we do that? It's a bit complicated to see it in the assembly, so let's put that into a function. Let's call that the get register. Okay, let's take it a pointer to an integer, for example. And let's just return that. Okay, that's what I get for not looking at what I type. So I can do this. So let's have a look at what kind of in assembly we got. And in this case, we're probably going to go back to Clang, which has a better thing. No, it does not. Okay, so let's go to GCC then. Yeah, so what do? We take the pointer and we load a YMM register, which is a register we use whenever we are in AVX2. If I'm going back to SSE 4.2, the code automatically changes. And now we are going to load into an XMM register. Now, if I deactivate the execution because I do not have an AVX512 machine, and I ask for some of those, so for example, let's say Sapphire Rapids with a proper number of P. Yeah, now we are loading up into a ZMM. Okay, so I cannot run it there because I don't have the hardware, but I can generate it. Let's go back to AVX2, which is happened. So we have these kind of things, and we saw that we can generate something very meaningful in terms of results. Okay. Another way to fill up wides is to use either a direct initialization by braces, it only works when you have the proper number there. So it's very architecture specific. The order is always a natural order, okay? Because some CD registers are little Indian, some are big Indian. We don't care. We store them correctly every time. Okay. As we already saw, then you can also fill using a formula. Okay. Either by having just the index of the current lane you want to compute, or the number of the ID of the lane and the number of lanes. So this is basically some kind of iota, and this is something that basically uses the total size to know how many things it can do. And so if we take that and we go back there, let's have a look at what kind of result we get. Yeah, if you execute it, that's important. Yeah, so we had 1, 2, 3, 4, as we expect. Then we have what? 2.3 times 1, 2, 3, 4, and so on. And we had 1 over 0, 1 over 0 over 4, 1 over 4, 3 over 4, and so on. And if I remove the size there, so we get 8 of them, we should get up to 7 over 8, whatever. Okay. And as I said, I can just, like ask for 32, for example, because we like that. Okay. Oh, yeah, sorry. If fixed. Yep, and we got all of that. Okay, which is probably what we want to get. Again, we can actually take that, make a small function and see what's going on. Okay, let's call that generate. Okay, and just say that we return that. So just in case, because I don't know exactly what are your level in C++ and modern things. If you have an issue about the lambda syntax or whatnot, don't hesitate, and I can answer your question later. Okay, what kind of assembly do we have there? Yeah, basically, yeah. We know that those things are finite. They are compile time bound. So basically what Clang does is just load a bunch of constants. And we have 32 of them by pack of 8. So we have 1, 2, 3, 4 operation. Okay, if I ask for 16, I got like 2 of them. Somewhere. Yep, okay, you have 2 of them. And if I have less, I will have an XMM with less inside. Probably. Yeah, we just saw that. We have 0, 1, and nothing else. Okay. Or 0.5, sorry. Yeah. So it adapts again. Okay, and we can get those values easily inside the thing. Okay. So much for initialization. What do we have next? As we said, we have a bunch of operators, a lot, functions, a lot. You can have a look at the documentation if you want, okay? Because we don't have time to go over all of them. But most of the time, if you need it, it's there. If it's not, you can find an issue, and we will tell you where you didn't look for it. And if it's really not there, we are going to make it, no problem. So what can I do? So I have a bunch of wide there, so I can do this. I can add 4 to every C, so that's broadcasting 4 to every lane of C. I can also do that. So every operator has an infix function notation, so add, sum, mul, div, and whatnot, bitown, bitor, so that they can support something that we are very proud of, which is our option system, okay, which is those strange square brackets on top of a function. If functions are actually not functions, they are objects, function, okay? So we use these tricks to add extra API on top of the function. So what does this mean? This bracket, A less than B, C4. Well, we are going to compute C plus 4, and put the result only where A is less than B. And where it is not, we are just returning the first parameter, which is C. We can do multiplication, and we can do what we call a relative masking. Okay, we are going to ignore the first two elements of the computation. So we are going to have C times B everywhere except for the first two values. You can call function, and we have a bunch of semantic modifiers. We have a lot of them, but the most useful are those ones. You can ask for a saturated operation. So B and C are added together, but if you go over the max value or under the minimum value of the type, you get clumped. Okay. Either it's done by doing the computation, or on some system, you have an intrinsic for that. So it was important to access them through a high-level API. You can ask for being pedantic. That means that we are going to handle more special cases that we normally do in exchange of less performances. Okay. So we are going to handle the normals better. We are going to handle corner case better. We are going to get as much precision as the standard could get and whatnot. You can also ask for a value to a function to be called numerically, which means that we are going to ignore nans. Just if you have a nan, we return the other values. Okay, and we have the row modificators, and now we have also a fast modifiers. That basically says the exact opposite of pedantic. We don't care about precision and whatnot. I just need to go the fastest possible. Row implies that if you have a single instruction way to compute this operation, but you lack precision or you lack corner cases, we are just going to call the intrinsics. Whatever corner case, we don't care. So you can go very fast. Okay. And obviously, you can combine those because you can put as many brackets you can. And a bit later, maybe this year, I think, we are going to support C++23 conditionally, and you could use the multiple argument brackets operator. Let's have a look at that by putting some value into it and look at what kind of operation and result we got as soon as I get my cursor back. So let's go back there, okay? Let's just do that. So we have our list of stuff to test, okay? And let's actually put some values inside. We are going to play around with different architectures, so we are going to try to fit them using functions either instead of doing this. Okay, so also because it starts to be a bit irritating, let's do some using namespace. Using namespace Eve. So we have a bunch of integers. Okay, so let's say that we have A. So let's say that A is like 1, 2, 3, and whatever. So it's I plus 1. Let's say that B is what? B is, for example, 10 times that. So I could also do something stupid like this, for example. So we have a look at that. You could write something like this. It's not very good, but it works. And let's see. Let's say C requires the size because we are going to return C plus 1 minus I. So we are going to have like 4, 3, 2, 1 or something. So let's have a look at those functions, at those values first. Okay, let's have that. I will try to go slower there if you want to replicate the code on your machine, so you can have an access to that. So 1, 2, 3, 4, 6, 7, 8, 10 times that, and 9. Oh, okay, the plus 1 is not required. Okay, that's better like that. 8, 7, 6, whatever. Okay, so what do we want to do? Let's do C plus 4. Let's just jump a line. And C plus 4, as we expect, should be 12, 11, and whatnot. Okay. Let's do this mask thing. Okay. So we are not doing the exact same one because it won't be interesting, but let's call add. Let's say that I'm going to add C and 4 if and only what can we do? B A is lesser than 3, something like that. Okay, and let's see what we got. Yeah, so we have 12, 11, and then we stop because now we are not less than 3. Okay, so maybe let's less than 5. Okay, we see that the computation stops, and we go to C. Okay. Okay, so now if I do that, for example, if I do it the other way around, whenever the comparison is false, we are going to get 4 instead of C, and then we get that. So we get this kind of control. As we said, we can also have multiplication. Okay. So the question is, why do we want to have this masking thing that low level available? Because on some system, it's basically the same cost of doing a masked operation than doing an operation. So it's very interesting to have access to those using a proper API. So C times B do whatever C times B does. Okay. And let's do mul between C and B. And let's do it only if, or let's say, we ignore the last 2. Let's do something different than what we have there, but just so we can see that. So we have a bunch of relative conditional: ignore first, ignore last, keep first, keep last, keep in between, and so on. So whatever the size, and that's why it's interesting, those relative masking adapt automatically to the size. I have 8 there, so the last 2 are not touched. If I go back to SSC2, for example, and we have like 4 values, and the 2 first are ignored. Okay, so that's an interesting way to do some masking. Okay, now let's do the saturate addition. Okay, which is another interesting things to do. So let's saturated. Sorry. Let's do B times B. Oh, B and B, for example, but it's not. It won't saturate. How much is that? 2 billions? Yeah, 3 billions. Right. Okay. I don't know. Oh well, no, I know. Let's take the largest integers and try to add A to it. Okay. Or B, for example. So let's do that. Let's generate the biggest integer I can get. Well, I know how to do that. I have a valmax function that takes the type I want. I want to be the same type as A. Okay. And that will generate the constant with the maximum value of int. So we got these things. Why? Because if I add something to the maximum sign value, I will get back to the minimum negative value. But now I can ask for saturation there. So it's not very interesting, but let's do that. And what do I get? Yeah, I get the max one. So okay, let's do something. Let's val max minus 2. So the first 2 can get in, but not the last one. Okay. All right, it's not probably enough. Yeah, okay, yeah, we get it. So we have a 46 and a 47 and whatnot. So we have a bunch of constants like that with this as function. So the question is, what is valmax actually? Because we just use it, but we don't know. So I want valmax in the same type as A. Okay, that's the way we read that. And it is whatever. So obviously, you see where this is going. We have malmean. We have very interesting constants sometimes. What's the name for that? Yeah, that's probably yeah. We don't have many much there. I mean, the integral constant there are not much. We are going to see what we can do with the floating point numbers. So let the thing compile. So we have the minors, the zeros, the whatnot, and so on. So now if we have a wider float, which is more interesting, let's say it's just return, I don't know, 1 over I. Okay, and let's have a look at what we have there. Okay. Yeah, we have a missing semicolon as usual. again, I mean, if you want to test that, you can have a look at the code and try to replicate that. So we have 1 over 0, 1 over 1, and so on. Okay. So what can we do? Oh, well, we can generate some interesting constant. So we can have minus infinite as x. We can have multi-subits of x. Let's have a look at that, for example. And we have a bunch of that. Oh, is it multi-sub? Not multi-subits? Multi-subits? Ah. Okay, I forgot where they are, obviously. So let's go to the documentation. Oh, multi-sub mask, obviously. Yes, multi-sub mask. That's the one I want. No, that's not the one I want. She's a lie. Okay, let's look for NB multi-subits. Okay. Yes, that's better. NB multi-subits. Number of multi-subits in a given values. So for float, it should be 33, if I'm not mistaken. Am I? I'm not. Okay. So we have those things. Okay. We have also a lot of EEE related function. So what do we get? There we got x, mean, square root, and whatnot. Okay. We could have a look at that. But by example, we can get that. So before I write something stupid, let's have a look at the documentation. Is it FRX? No. LDX? Yes. Is it? Oh no, LDX is this one. So it's not the one I want. I want the other one. It's not. Okay, I don't know. So you know what? Let's see if I find it somehow, probably in core functions, EEE except for operation. So what do we have? Byte of size, exponent. If FRX. That's the one I want. Okay, yeah. For some reasons. So what does it do? Again, before doing something stupid. EFRX. Yeah. So it slice. Compute the multi-size exponent. So I want the multi-size exponent, and I want EFRX of x. And so I can have a look at the multi-size and the exponent. So that's for the people over there that do maths. They like to do tricks with the EEE 754 representation. Yeah. And I got what I got. It's probably correct. I don't know. Yes, 129 for if and whatnot. See how we can structure bind the result, but we could also have the thing as a single value normally, and that will be in for later. And we have some sort of wide of pair. And yes, it is exactly a wide of pair, which is actually stored as a pair of wide because that's the way to do it. And this is one very important point. If you want to have a list of silent differences between all the other library and Eve have a natural support for data structure. We are going to see that a bit later, but you can have a wide of some tuple if you want, and you can do whatever you want with the parts. And it's naturally stored in a SOA order, so we can get proper performances. And so on and so forth. And we can play around with all those functions and operation this way. Okay, so what's next? We also have something which is very important to understand, which is the shuffling operation. As I said, you can look at register as some sort of small arrays in the hardware. And one operation sometimes you need to do is to shuffle around the value inside the register. So if your register is 1, 2, 3, 4, you can shuffle it to be 2, 4, 1, 3. Okay. It's not by using a pattern, but it's not very portable, or by using a pattern function. Okay. So you compute some reorganization of your things. And sometimes you have what we call a name shuffle or name swizzle. That lets you actually apply some correct operation on that. So you can reverse the value and so on. So what is the usage of that? Sometimes you are going to want to load data, but they are not in the order you want for the operation to make sense as an SCMD operation. Okay, right? So you are going to try to load that in a bad manner. Okay. So what you are going to do, okay, is to load your data badly as they are, okay, and find a way to reorder them, okay. For example, if you do computation over sparse matrices and whatnot, okay, you can get use of this. This is a more advanced element in the API. Okay, so we are going to pause there. It's almost 1 hour and 30 minutes. Okay. As I said, you can ponder, play around with the documentation if you want. And I would say that. Play around with the documentation, play around with the function, try things and write stuff. You have a mat.cpp file that you can actually play around with in the container, so you can play around and have some actual measures of performance of our operations. You are going on a break, and after the break, we are going to speak about algorithms and more complex operation over data. Okay, so enjoy your break, enjoy playing around with the library for now, and we are going back in a couple of minutes. See you later.
Okay, thanks, Joel. So we'll... No, not yet. Wait a bit, Joel. Stop. That's enough, Joel. We'll wait 40 minutes. Come on. So yeah, we will have a little break. So we'll enjoy the 40-minute breaks. We will start again at 11. So we are a bit in advance, but that's rare in the Grace Code, but so it's a good point. We start again at 11, and then we will do other stuff with Joel. If you have questions, normally everything is answered on Discord, so I'm pretty sure there is no question left. Normally everything is okay. So enjoy the break, and see you at 11. Okay, so we are back on the Grace Code School. So we'll continue a bit of wizardry with Eve, with Joël, so for a bit 1 hour, and then we'll continue the school and the wizardry with GPU after that. So Joël, it's up to you. Yeah.
And welcome back, everyone, for this second part, for this Eve courses, discovery panel, and so on. In this next session, we are going to speak about how we can use Eve at a slightly higher level using algorithms first. And then we are going to try to see how we can use Eve in non-trivial settings, like dealing with non-trivial types like structured data, and how to write codes that we like stencils and things like this. Okay, and so we are going to see how we can go up to having archetypal Grace Code implementation using Eve. So we saw just before that we have a lot of functions. We can use them with different options. We can use them on different types. We can handle different size of register and whatnot. So the question is what if I want to express more complex situation? And the classical way of doing this in C++, in modern C++, is to use algorithms, standard algorithms, range algorithm, and so on. So Eve provides a selection of SCMD, aware, let's say, call it this way, STD-like algorithms, okay, that will be able to handle for you all the complex tasks of running the loop, ending alignment, ending the tail at the end of the loop, and provide way to tune the algorithm depending on the architectures with respect to, for example, the way you want to unroll the loops, or even if you want to unroll the loops, how you can manage the problem of performances with AVX512 cores and so on and so forth. And we have a slight, a lightweight data structure to handle with that. So we are going to see a bunch of those, a bunch of algorithms, a bunch of views, and we are going to speak about structure of array and how we are in Eve very committed to this model of programming. But before going into the deep end of that, just try to see why we want to do this. Because, probably I can take any standard algorithm, that lay around, and just either let the autovectorizer do its jobs because it's there for that. Or maybe I can use, std parent sec or something like that to force my compiler to generate unsequenced and so forth vectorized algorithms. And so probably whatever we do there is useless, okay, right? Yeah, except not. Let's have a look at a very simple algorithm, which is findIf, okay? So in this benchmark, we try to find a zero in an array of 100 bytes, okay? So the size is very small because we want to be sure that we are not affected by L2 cache miss and whatnot. It's in bytes, so we can see the impact of the actual size over the basic benchmarks. So basically, the blue line is ST-defined, and ST-defined takes sometimes about 240 something for char, down to 80 something microseconds for 32-bit integer. And we see that the bigger, the object we are looking for is, the faster we go because we consume more bytes per cycles, okay? And what happened is that if you run Eve algo findIf, okay, that will vectorize, okay, findIf, okay, a different way to do that. Well, we don't care because we are always consuming 128 bits, what's inside, okay? So we have this very flat just below 10 microseconds of runtime, whatever the type is, which is on AVX2 a speed up of about 23 or something for chars and around 6 or 7 for integers, which is quite good. But okay, that's fine. But if you look, and that's what we are going to see as an example, if you look at other, let's say, easier algorithms, like transform, reduce, and stuff like that, maybe we are not going to be that good. And indeed, we are going to see that depending on what happens in our loop, our best shot will be to be as fast as the autovectorizer or slightly faster. And on the other end of the spectrum, maybe there is, like algorithms that make no sense vectorizing or for which there is no way to get forward the, performances. Oh, I know which one. Remove if, okay? STD remove if. You pass it a data set, you pass it a predicate, and you remove the value from the data set if it validates the predicate. And what you get at the end is a compressed data set where every surviving values are close together, there is no holes, and you return the end of the now compressed data set. So there is no memory allocation and so forth, but we have something that we don't know each iteration how many value we are going to keep. So definitely this is not something we can vectorize. Well, turns out, we can actually. I won't go into the details, but let's just say that there is a way on almost every architecture to do this compression quite fast with different mechanisms. So sometimes it's an intrinsic, sometimes it's a trick using shuffles, okay? But we can do that actually. And we have a very nice benchmark there. I like this very much. The time there is drawn upon the percentage of value that is equal to the value we want to remove. And we have these scalar bumps around 50% because what happens? Well, at 0% stuff to remove, you never do the if. You always take the if the correct way, so you always predicted your branching correctly, and so you go fast. And as soon as you go up to 50%, your branch mix prediction increase, so your speed decrease. And as you go down the other way around, you start predicting that you need to take the other branch of the loop, of the if, up to 100%, where basically you are fast also. So it depends on branching. But turns out we have a way to branch in SIMD mode. Okay, we have a function called if-else that is vectorizing if-else. Okay, and we don't care about the branching because there is no branch. Okay, it's all conditional execution of the code. And so we have this very flat at the bottom speeds. And so this is about 1,000 microseconds compared to 25,000 microseconds. So again, a speed up of about 24, which is good on this machine. So we have this very large setup of algorithm. I wish I could show you the documentation. It's currently a bit sparse due to some doxygen errors we are trying to find out. But we have a bunch of them. Let's see if we can actually just have a quick look. Let's go there. Okay, and just so you can see the how to say that, the scope of what we have. Where are you? Are you there? Yes. Yeah, so yeah, we have a bunch of them. We have predicates, we have copy, if equal, fill, find, for different versions of for each, inclusive scan, iota, keep if, which is basically remove if the other way around, computing of min and max, mismatch, none, and so on and so forth, and reduce, and a bunch of others, transform reduce also, which is very interesting. So we have a large selection of algorithms, and we also have a large, less large, but large anyway, selection of view like zip, reverse, map, convert, and so on that lets you look at your data set in a way that is actually more complicated than that. Yeah, so we can do that. So let's have a look at how it can actually work on an actual use case. Let's say we have that. Okay, we have this process scalar function. It does some computation. Okay, And what you want to do is you want to use if to vectorize it. So we are going to transform input into out, okay? And we call this lambda. Okay, so I'm trying to go very slow because the process is very complex. So you can do this, and you do that. And what you want to do is call if algo there. We actually have two transform in place and transform to, because there is a slight optimization we can do there. And we are done. So let the thing compile. And it should be practically done. So this is where I should have put a small, elevator music in the background, but here we are. And as I said, there is no surprise. We have a speedup of basically nothing, because I hope every compiler is able to optimize that and auto-vectorize it. Okay, and so if we have a look at what the auto-vectorizer does, it does something. It even knows that it can use that. That's cool. What do we do? Oh, and then it does the tail. What do we do? Well, we do some stuff at the beginning. We are going to speak about that later. And then we have 1, 2, 3, 4. We have unrolling by a factor of 4, okay, which is basically there. And if we look, we mul sub add div. Oh, turns out we don't use FMA. Okay, but that's something we can easily fix. We are going to see that. And the actual interesting thing, this is actually, where is it? Yeah, this is actually the compact loop. Okay, this is what is going on in the innermost loop. And so the question is, what do we add before? Because if you look around, I know it's a bit complicated, but if you look around, there is no mul SS. There is no scalar computation. We are going to go back on that a bit later. So, or maybe I should unroll a bit less, because if I look at the regular cases, the auto-vectorizers didn't vectorize. So we can actually, because if algorithm, like if function, are actually callables, we can put some options there. And so we are going to use the unroll function, the option, to say, okay, what about I don't unroll? Can do that. And yeah, we are going to compile for a bit. So a bit more elevator music at this place. So Pierre, if you are in the back, probably we should hire some kind of, orchestra for next year doing this. Okay, we are slightly better. So apparently not vectorizing helps. And as we see, the auto-vectorizer know about FMA, and apparently we don't. So let's teach that. So what are we doing there? We are going to do E times E plus 1. So this is a multiply add in the correct order. So let's just call multiply add. Multiply add between this and 1. Let's see if it goes faster. This is another issue, but let's see if we go slightly faster. We are already 10%. Oh, that's worse actually. But we were actually 10% faster at, like a few seconds ago, so it's not that bad. Let's see if FMA actually helps. The game is how much things should I write to get close to whatever the auto-vectorizer was doing. So it's slightly worse now. Okay, fine. Probably because we need to complete the thing. So this is multiply sub. Okay, and so we have the whole, we have the whole family, like multiply add, multiply sub, add, multiply, sub, multiply, negate of multiply add, and what else? There is like 6 or 7 of them. So we are at what? 5%. So we are back to where we were. Okay. Let's see if I force a recompilation. So another great thing so you can do, yeah, it's not that good. Okay. Another great thing you can do using Eve is that you can use evalgo to get some free time, when you want to do something else while we compile. You know what? Let's see what we can do there. What kind of other option do I have in my algorithms? Where are you? Okay, let's dive into this. So we have a bunch of options. So we saw nothing there because it needs to be like very bigger than that. So we have the unroll things, okay. We can force the cardinal of whatever we want to compute. You can force the type in which we want to compute. That's another thing. And I'm trying to find out. So non-rolling is basically this. Yeah, no aligning. Because if we go back there, okay, and we have a look at the small thing there, we saw that we do a move, we move an align, okay? We load an align data because the auto-vectorizer doesn't want to care about whatever this thing is. What we do is that we try to care about loading stuff aligned as much as possible. And so we have some prolog up to the point we know we can actually have a full-blown, where are you? A full-blown, alignment, loading, and storing, and whatnot. But this adds a bunch more computation. It's not a line anyway, so maybe we can just tell the algorithm that we don't really care about all these aligning things. So we can probably say just don't align, just don't force the alignment of yours that are set. Okay, so let's see if it's better. Okay. So one thing we try to do, as you see, is to isolate the fact that you want to write the actual math there in a way which is orthogonal to actually writing, the definition and whatnot. So we are basically at the same thing now, which probably means that we generate probably the same code now. Okay. What is that? Okay. So this is the main loop. Okay. Now we load an align, and then we have this. We try to finish what we started. Okay. In these cases. Okay, and because we don't enroll, but we don't know how many things we have, and so we have then the end of the tape. Okay, so we are basically at the same speed now, so which is exactly what I expected to get. So we saw that we get a small amount of changes, but this 10% is actually not meaningful. We are basically going at the same speed. So let's do the devil's advocate. So all of that for nothing. That's very cool. Thank you for playing. Okay. Obvious, but it was obvious we are going to go there. Now let's see what happens if we do a bit more complex operation. Let's just be mean and say we need to compute this. And then we can say, oh yeah, I know how to do that. I can just call fx there and see what's going on. So most of our complex function, complicated function, I need to be careful with the things I said, is like exponential, logarithm, trigonometry. They all are based on some different kind of polynomials or sub-series approximation, okay, depending on what we do. Sometimes with a reduction of the input, so we can compute stuff faster and then reconstruct the real value. So it's usually better than whatever the poor auto-vectorizer is going to do. So if we do X now, we have a bit more computation going on, and we saw that we start having a speed up of about almost 5.8, which is almost 6. We are dealing with AVX2 register of float, so we should have a speed up of 8. So 6 over 8 is what, 72%, something like that. Okay, we could actually compute that in the display, maybe. Let's do that. Let's compute the efficiency of these things so we can get that, because I will spend my whole hour trying to guess how much is that much percent. Okay, so efficiency. So this divided by what? Wide of float size, probably. So we have something which is actually architecture agnostic. Okay, and this is percent because it's efficiency. Yeah, so let's do that. So, okay. So if we go with more complex function, obviously, we start having a bit more interesting speeds and so on. Yes, so did I forget to multiply by 100? I did forget to multiply by 100. whatever. So we can do that. Okay, that's the way to do this. But exp is a complicated function. You've got a bunch of corner cases, and the if exp, like a lot of basic math function in if, it tries to do its best. Okay, right? And as we saw, we have way to make it faster. Okay, we have different level. We have the raw level. We have the fast level that can ditch precision or whatnot to get better speed. So let's see what happens if I try to do that the stupidest way possible. So if you want to play at home, try to think how you can actually compute the exponent of something, okay, without doing some Taylor expansion or whatnot, or using a proper Remez expansion of these algorithms. Yeah, so we got like 13 speed up. We got twice faster, so we just blew up the thing. We blew up the speed up because we go faster because of SIMD, and we go faster because we have a funky algorithm. The funky algorithm is based on the EEE 754 representation of a floating point. So there is a funny way to compute this by forcing the exponent into the exponent bits. Okay, so it involves bitcast and whatnot. It's a funny algorithm to write. So let's see what happens if I don't know, if I remove that, if I remove those options and I go back to this very simple function call. So we were at times 13, which is not bad. It's basically times 10 and some bonus. So it's one order of magnitude. And again, okay, we don't do any OpenMP, we don't do any MPI, we are not on the GPU, we got the 10x from our own CPU. That's exactly what we want, right? Slightly better for some reason. Oh yeah, X is probably big enough, so we have more opportunities of, you know, interlacing things during the enroll. Okay, fine. So we can do that. Okay, and again, the cool thing is that the math is there. Okay, we can decide to do this. Let's see what GCC does. So let's say 14. Okay, 13.8. That's a good score. Let's see if GCC is better or worse. Maybe GCC know how to vectorize X. Maybe not. We don't know. That's a surprise. Yeah, well, spoiler, it does not. Okay, and so we are slightly lower with GCC, but it's probably just the variation of the whatever. But the question I have actually is maybe GCC is a bit smarter, and does it know about the FMA there? That's the question. Sometimes compiler sees that you have an FMA and it generates an FMA for you. Sometimes it does not. We strongly advise to, if you really want to get the bonus point from FMA, to call it explicitly. Okay. We could also play around with the data size and whatnot. But yeah, so do we have a FMA now in our vectorized code? Where are you? That's a lot of people going there. Okay. Am I inside already or not? I was. Okay, no. Processing this. Yeah, I was not. So what happens? Do we get the... Oh, we get the free FMA actually. So GCC sees the FMA, generate an FMA and whatnot, and here it goes. Okay. Let's see. Yeah, in some other place it does not, but yeah, it does the thing. Okay. So depending on the compiler, sometimes you don't need to have to put it, but it's clearer. So if you put it whenever you want. So let's go back to Clang. Clang was slightly better actually. We could play with lesser extension or bigger one if you want, but we are going to be around those time 14 something, which is not that bad. Okay, yeah. But then again, and I think I heard the question or the remarks last week when I was scouting the Discord channel. It's all fine and dandy, but what if I want to do something a bit more complicated than that? Because I'm all for processing floating points and double and whatnot, or integer in a single vector, or a span, or whatever. Turns out sometimes I need to have, I don't know, like a 3D position, or I have to have a pixel with tricolor as unsigned char, or whatnot. Okay, stuff like this, actual data structures. What do we do with that? Well, yeah, we need to work around that. Okay. So this is something we need to have a look at. Where am I? Okay. So let's see how it works by trying to do something very simple. What about I want to work with, let's say, STD complex? Very simple stuff. I need to have a complex number. Okay. I want to, I don't know, like compute its norm using iPod or whatnot. Okay. So we can actually do that. Okay. Let's. I'm going to spoil that for a while, and we are going to see how it works. So this benchmark is a bit more complicated. I put some optimization barrier so we can have an actual benchmark run that works. Okay, so you have that in your example file. It's not very important. It's probably something you already spoke about and whatnot. So what do I want to do? Well, I have a vector of complex float coming in, and I want the vector of its magnitude. Okay, so I'm going to do what everybody should do, computing the iPod between the real and the IMAC part of the complex number. It gives us some codes, okay? And actually, if we go down there, let's see what process scalar looks like without doing anything. Yep, whenever. So iPod is basically the square root of r squared plus I squared, but with proper precision and handling and whatnot. So you don't end up with none or nth as soon as your complex number are very close to 0 or I or stuff like that. So whenever you want. So what does process scalar does? Yeah, it completely drops the balls because it's just called iPod. So now that's the place where you should remember about fast math. This is probably because iPod touch the global error code whenever you do something stupid with your value, so it has to do this. So normally we should win a lot. But the question is, how can we do the same thing? Okay. Well, let's start with something simple. I know how to write SIMD code using Eve using regular types. So I can actually write this. I'm going to take a function with two vectors as an input. So real and IMAC part. So we manually somehow force the code to be into some kind of, structure of array, separated mode. Okay. And so, a bit like we would have done that using STD algorithm in view, we can zip the two vectors. Okay, so now this element is actually some kind of a tuple that contains, as we saw there, every time both a part from real and part from IMAG, and then we call iPod. Simple enough. Yeah, but what if I want to have something that actually behaves like a complex? So turns out that Eve wide is compatible with types that follow the tuple protocol. So tuples, okay, or tuple-like object, stuff like pairs, okay, and whatever struct for which you manually implemented the tuple protocol, which is having a get function, having a tuple size, a tuple element, and whatnot, which is the basic way we have since C++17 to make our data structure able to be used that way, by the way. Turns out, inside Eve, we use another library of mine, which is called Kumi, which is a small large reimplementation of tuple and tuple algorithms that happens to be out of the block compatible with Eve. That's a good idea we had. So let's start simple by saying that a complex is basically a tuple of two floats. Could have been a pair or whatever. Okay. We are going to see what happens if you try to use STD complex by itself. Okay. So it's a pair of floats. So now what I can have is I can actually have not a vector of complexity, but this thing, a SOA vector of complexity. If SOA vector is a container that behaves just like vector, except it only accepts types which are actually compatible with the tuple protocol, and it will automatically behave like vector, but store everything in an automatic SOA manner. So we have a SOA vector of complex. And basically, we get whatever the complex is there, and we can pass it to iPod. A lot of if functions have these properties. That is that if you have a regular element-wise operation like add, mul, iPod, square root, and well, square root is not very useful, but stuff like this, power, that takes multiple parameters. You can also pass a tuple of set parameters directly. So if you want to multiply 5 elements, you can pass 5 parameters to mul, or you can pass a tuple of 5 values. It's a sort of compile time broadcast, if I can say that, or compaction, depending on the way you saw it. So we have a tuple-like object there, so we can pass it directly to iPod, which is very similar to what we, it's actually better than what we did there, because we don't even have to unpack it. We could, but we don't even have to do it. And iPod is a very complex function again, and so we can actually ask for a faster iPod. What's the difference? This is doing a lot of precision handling, okay? This is basically square root of the square, the sum of the square of the parts of the tuple. So this is very, very, very raw. So if you have stupid values, you get stupid results. But it goes faster. Okay. And again, we can wrap that into transform 2 using either something that is already a SOA container, or we can build your own using zip. Oh, and by the way, because I saw people probably in the back trying to raise a question, yes, you can zip whatever type you want. I could have made a tuple of 2 floats and a char and whatnot. And we know how to compute the best number of lengths for this composite type. And you don't have to do anything. Okay. So in this case, yeah, we got float because it's complex of float, but we could have more complex system like this. Okay, and then we bench. So what kind of result do we have? Well, not that bad actually. So the Scala version takes about 1.40 something, 46 something milliseconds. When we zip it using the regular iPod, we go basically almost 8 times faster, 7.2. That's, oh, come on, I should have put the thing back. I forgot about the efficiency, which is the only interesting metric there. Let's have a look. How much is that? 7.28 over 8? Yeah, it's like 91% efficiency. That's good. Yeah, that's good. Zip and SOA basically do the same thing because internally it's the same thing. Okay, add some details, but I mean, as the third decimals. And when we say that we don't care about the precision, because most of the time when you want to go fast, you don't care about precision that much, you can go actually 20 times faster. So if you have very well behaved complex values, very close to magnitude of 1 or something like that, you can actually raw iPod them and you can get like 20 times faster. Okay, but we spoke about it. What if I sabotage myself by putting a fastmat there? Normally, the autovectorizer should do better. That's what we think. But does it? Okay. And are we able to have some leverage against a code compiled with fastmat? Eve is actually able to detect fastmat itself. And so whenever you compile with fastmat, we say, okay, you compile with fastmat, you know what? Maybe what we are going to do is to use the row or the fast lane directly because you just gave us the permission to do so. So we also know how to interact with those compilation options. So what does process scalar does? Yeah, it doesn't do anything. Okay, so Clang doesn't know how to vectorize iPod even using fastmat. I'm kinda sad about that. And we get basically the same results anyway. So it's not a case where we can win much there. Okay. So we can do this. But, I mean, maybe complex is already compliant with the, the tuple protocol. Let's have a look. Let's try to do this. If it is, I should be able to do that. RI about SED complex 4.5 and 6.60 point whatever. We don't care. I said we don't care, but a bit more than that. So does it actually compile even? That's a question. And apparently, nope. Oh, the solution guide. Oh, come on. Come on. Okay, one more deception. Yeah, I mean, yeah, binds one element, which is very strange because it should be, you know, right? So complex doesn't look like it does. Let's start to see if we go further in time. Because I remember having a discussion about that recently. So let's see. Yeah. SLE complex is not compliant with the tuple protocol. So we are a bit screwed. Yeah, he's not very happy about that. Yeah, I mean, we break a lot of things. Let's see if GCC has a bit more leverage on that. There is a paper about the fact that complex should be a tuple, but I don't know where it ends up. The answer is nope. Okay. So whatever. So too bad for us. We can even do that, so we can do this. That's a bit of a pity. But you know what? That's not that big of a deal. So as we said, we can do that. Okay, that's the complex number stuff. So the variant we have. As I said, in this place, I unzip. I just destructor to pass it, but as we saw, we can actually just pass it directly. And for those of you that are very sad that STD complex, sorry for the strong word, is basically a pile of manure. Okay, we have a Eve adjacent library called Kiwaku, which implements some kind of Kali-Dixon algebra for computing over complex quaternion, octonion, and whatever is beyond octonion if you really want to. Yeah, it's basically complex, but with a decent, thing. So you can find it on GitHub if you want. It's still not. It doesn't have a release yet because we are still working on the documentation. But let's if we look at the example, that's exactly not where I wanted to go. Just so you can have a look at that. Okay, not there either. Doc. Yeah, we have a bunch of whatever, including those big functions, stuff that makes sense when you know what it is. Let's have a look at, I don't know, what X. Yeah, we can get that. Yeah, so we have the complex, the quaternion cases, and we can mix match wide, scalar wide, and whatnot, different kind of concept, and we can just use them directly as a type inside wide, and we have a SOA implementation of those types. So if you want to have a look at that, you can up there and see if you like the things. Yeah, so we ended up having to do that because SLE complex was a mess. It doesn't have like half the function we need. The reason why we have that, so you can see the bigger picture, is that we are also working on a library called Fluxio, which is not out here, which is basically using Kiwaku and its complex and quaternion numbers to implement some kind of forward scheme for automatic differentiation, whatever, and all vectorized. So we have this kind of expansion that goes over there. So if you want to dig these complex things, you can have a look at that. But let's do something else. What happens if I have a more complex data structure? Like, let's do some high school physics. We all, know and love our good old Newtonian physics. Okay. I should make an example with relativistic physics at some point. But basically, what I want to do is that I have a ball. My ball have different properties. I know where it is on the z-axis. It's a position. I know what its speed is along this axis. It has some elasticity coefficient because it will bounce back. And I'm going to count how many bounces I'm making. Okay. And so what you can do is you can use Eve through his Eve struct support struct to do a bunch of curiously recursive template patterns there to say that your ball is actually that. Okay, 3 floats and an integer. And this gives you everything. It gives you the data set inside, which is a tuple of all of that, and it puts all the required types and overloads so that it's tuple compliant and it's Eve compliant. All those functions are basically just helpers. You don't even need them because you can std get directly on it. But it's better to have them because we get a bunch more, semantic. We have this concept like T that basically says that you can pass whatever there as long as it's either a ball or a wide of ball. Okay, that's the way we can consume both scalar and SIMD type of this. So this is an actual SIMD-enabled data structure. So now we can do some simulation. So I have a ball coming in, and I'm going to do some very bad physics there. I should be using some actual integrator, but I have only so much time. So I'm updating my position by taking my delta time and multiplying by the speed. I put the gravity back on the speed, and then I check if I bounced. Okay, if I bounce, I'm going to switch my speed sign and multiply by some coefficient, and I count at the fact that I bounce. So if you look, I update the falling ball and I compute the new bounce ball cases. And then I need to know what happened after my update step. And what we say that if the position of the falling ball is very close to 0, we are going to snap on some grid, and we say that we are going to bounce. So we use the bounce value now. Either we are going to use the falling balls. And we have this if-else coming up. Okay, they say, okay, if this is true, I'm returning this or I'm returning that. Okay. And so we have this simulation step. Now what can we do? We can have an object of update. Say, okay, I have that dt, my gravity is whatever, I have some maximum amount of bouncing. What do? Well, I'm taking my SOA vector of balls, I unroll a bunch, and I transform it in place using the behavior object. So for every ball into the balls vector, we are going to vectorize this operation of simulation and update it. And after some amount of bouncing, we consider that we don't care about some of those balls, and we remove if. That gives us the end of the memory space where the correct data are set, and we do an erase from there to the end to remove them physically. That's the classical erase remove idiom, okay? That still work on our SOA vector of whatever. And what happens if we have a look at the function itself? Well, a bunch of things happen, but at some point I have, where is it? Some sort of very dense loop. Okay, that's the main loop. I need to unzoom a slightly tiny bit. Yeah, so we go from there to there. And we have the mud, al, sub, zor, mul. This is some computation of comparison, and then we update. So this is basically what happened there. So this is AVH2. Let's put some FMA inside. Do we get the FMA? I don't think we have FMA. We don't have FMA, so it's probably useless. Oh, I know what we are going to do. Yeah. So let's see what happens if we go like Sapphire Rapids or whatever. Some big ass, LX512 architectures with a proper number of P. That's probably that. So I don't touch the mat. I don't touch anything there. I'm just changing the compilation option, and I get a new compilation with different subset of intrinsics. I'm not going to make it run because it's a bit long and it's not very funny if we don't have any kind of display. But you have it in the Eve examples in the GitHub, and so there is some actual bouncing display. But what happens? So what happens? I ask for AVX512 and I end up with AVX2, which is okay, but that's not what I ask. Yeah, because AVX512 causes CPU to slow down when you start processing AVX512 intrinsics. This is the AVX512 speed penalty. That is something that is, alas, well known. But turns out we know about it, and we have different way to get around that. Okay. What's the name? Oh, frequency scaling. Okay, here it is. So we have yes, we have this option. Okay, where are you? Is it you? Nope. Is it you? Nope. So that's you, yes. So I can ask transform in place to be called with what we call the frequency scaling option. That say basically I don't care about whatever LX-I12 is doing. Okay, I just want to go faster, and I want to have LX-I12 things going on. Okay, and now do we have some ZMM going on? Do we? So we have Y there. Oh, did we fail again? Oh, we failed again. Oh, come on. Oh, yeah, because I'm stupid. Okay. I'm not at the correct places. Arch equal. So if we don't use LXI12, obviously we don't use Sapphire Rapids. Sorry about that. Oh, I probably duplicated the window. So if we allow for frequency scaling, that's basically only have any meanings on x86, but here they are. We should have some ZMM going on. Okay. And do we? Yeah. Now we are running LXI12. Is it better? Is it not better? We have to test that, but we know how to generate it also, and we got whatever we need to get there, including where are you? Where it is? Yeah, including some conditional move and whatnot. Okay, so we can go that far in terms of data structure handling. Okay, so we do data structure. We do where are you? Oh, I lost my slides. Do I? Did I? Oh, I did. Oh, because I probably do this. Yeah, I did. We do that. Now, what happens if I want to do something other? Let's talk about stencils, because we know we are going to do stencils at some point. So this is another filter. This is the bilateral filter. It's a funny one-dimensional stencil operation that you can use in image processing. It's basically some kind of smoother filter, but that doesn't generate sharp edges whenever you have a big difference of intensity, by using some exponential computation. Okay. So we saw that it's a stencil because we have this I plus J thing. So we have some kind of a neighborhood there, and we do this exponential compute a weight, we do some weighted sum, and we finally end up, doing this. So it's a 1D filter like that. So how do we handle stencil using Eve? Currently, we don't have any stencil-enabled algorithm because I will be very frank with you, it's very complicated. You can emulate them using zip, but you don't get good performance out of that at some point anyway. So what do? Well, for every point of the stencil, we are going to load a different wide, and then we are going to replicate this exact computation, inside a wide. So we load some data from the image, we do the same computation, loading with the same differential position, and we do the same computation, and we do the x and whatnot, and we do that. And as we do it by hand, we need to handle the tail ourselves. Spoiler, if you have to do that, look that my scalar version takes a span and not a vector, because I can then reuse it as a tail handling by computing some subspan from my original span of data. That's a cool trick because you don't have to duplicate the code about that. So let's have a look at how it looks when we try to run it. Okay, so this is not that. This is not that. Nope. Yes. So that's the bilateral filter benchmark. Okay. So again, that's the one you have in the Docker. You can play with it, play with the radius and whatnot. This is a very big radius, by the way. Okay. And yeah, we have exactly what we saw. We have two variants from Eve: the regular one that has the regular x and the one with the raw x, obviously. And we see that we got some decent speed up there using what AVX2 and FMA. Okay. Speed up of 4.3 something because X is costly, and if we go the row X, we go better. And in this case, using a bad precision X is okay because we are generating pixels in the end. So your eyes is not going to see any difference anyway. So we can do this. We can do stencils. But in 1D, it's easy because we can do one stencil per whatever, okay? Let's do something while I'm speaking, okay? What if I have a very small radius now? When you have a 2D stencils, like we have in the Grayscott operation, you see that you have to have, if you have a 3x3 stencil, you are going to need to load explicitly 9 wide. And if you have two things like the, exactly like the Grayscott, the U and the V, is it done? Oh, yeah, it's done. So it's basically the same thing. You are going to need a way to manipulate this large amount of whites. That's why we want to have something that is actually common. Workable as, yeah, we don't care about that. Where are you? Oh yeah, I know it's not there because I need to run it on my actual machine. Let's just have 1 sec. So let's see the code on my actual machine because it's not going to fit into the thing. So again, you have that into the Docker so you can play with it around. So we have some, preset like the size, the value of the coefficient and whatnot. Here, I hope they are the correct one. If not, I will look stupid, but whatever. Somewhere else, we're going to have our stencil, which is basically over there. So we have those points, okay. We got some utilitarian values. We don't really care about that. And so we have this 2D 3x3 stencil going on where we read into U and Y, we do the computation, we do the update of the output, we update the border and whatnot. Full-blown things. Then we can do the same thing with Eve, and we decide to do a bunch of unrolling and a bunch of FMAs and whatnot. That's the core kernel. We load U and V, we do some computation, and then we load every other parts, depending on where we are in the U and the V. And so we get multiplied by the stencil. We do some more FMAs, and so on and so forth. We could actually probably be able to factorize all of that, and then we do the computation, and we store at the end. We have another one where we put FMA and FNMS everywhere, okay? And then we have the bench things, okay? And so the question is, how much do we get? So let's see how it compile, okay? Oh, yeah. That's probably a good idea to add some kind of, include pass. I forgot about that. And by the way, so we are a C++20 library. I didn't speak about it. If you forget about that, we get an error message that say you should enable C++20. So, okay, so how big are we? Let's see. So, scalar, some FMA, some enrolling, some more, and so on and so forth. Let's see what's going on. So we have 2 levels of unrolling, different way of handling FMAs and whatnot. If you remember last week, you should see that it may depend. And so the scalar is actually auto-vectorized. So we have to be very careful with the number we have there. This thing is auto-vectorized. Yet, when we use some mix of stuff, we can get to 1.6 times faster than the auto-vectorized version. Okay, fine. Let's go over our FX512 machine, where normally I should already have, I already compiled some of those. Let's see if it's the same version. Yeah, that's the same version. Oh, we don't have the mixed one there because we know what we should be doing. Oh, I can actually take that and recompile it completely. Okay, let's see what happens when we unroll or don't unroll and see how far we can go there. Okay. Okay, $10. It's not the correct version. Yeah, no, that's not. It's not working. Okay, let's do that. Probably not the correct version. Not a big deal. Let's do this exact same version. Okay, and yeah, let's go up there. Yeah. Oh yeah, I know why it's not good. Okay. At some point, I tried to get something like with different level of things, but it's not what I want to do. So what am I? I am a rocket lake. This one is a rocket lake. So let's do that. And we should have something comparable. If I'm not mistaken. Yeah, that seems better. Okay, let's go. Yeah, and we go twice as fast as the auto-vectorized version with the biggest things of 800 and almost 10 megacells per second of update. So even in the face of a complex how to say that, complex operation with slice, with stances and whatnot, where the auto-vectorizer is able to do great things, we are able to get some decent extra performance. You can play around with it, play with the size, play with your architectures. Let's see how it behaves. Okay, it's an interesting thing. So it's probably time to conclude now. So what did we saw? So we have this library called Eve. It provides us a path to explicitly vectorize code by also providing some guarantees about the performances. If you write regular code with regular operation in a way that makes sense in terms of CD, we got you, and you got some decent performance. We have extra API for algorithms, for data structures that we keep improving, okay? And so we can actually play around with that. We have tag release. We are closing up to getting an actual version 1, probably this summer, now that we know how to compile on Visual Studio and fixed a bunch of API issues. Okay. So I encourage you to test it in your own project if you're interested with that. If you have bugs, just report them. We try to solve them as fast as we can. You want some function, you want some architectures. We are all open to add things if you want. If you have strange hardware and you want to support it, if we can have access to it, we can probably make a port, and so on and so forth. The workflow we recommend is trying to find the places where, after, for example, a benchmark or profiling, you see that you are lacking vectorization while you should have it. Okay, so a big shout out to the people from Macau, for example, that are very useful to find those cases. And so you can actually extract it into a standard component, vectorize it using Eve, put it back, and you can see any improvements. And in any case, anyway, if you are confused, if you don't like performances, you think you had a bug, please don't hesitate, ping me or ping the team, and we are going to fix that. So as I said, again, big sorry for not being there in person. I wish I could have. Thanks for your attention, and I will be available this afternoon over the Discord and the rest of the week. So don't hesitate to contact me, to contact us, and yeah, just in case, because before I forgot, we also have. Yeah, we don't care about that anymore. Sorry. We also have, where are you? Yeah, we also have a Discord. So if you want to get there, for example, we are very, we try to be very keen and accepting. So don't hesitate to come over and we can discuss all of that. So have a good, have a good end of the week. If you want to try much other stuff, don't hesitate. If you're also interested into getting in more depth around that, you can over codeicons.com if you want to get more information, more trainings about this subject, and we are very welcoming for new users. So have a good week. I will wait your question in the Discord. Don't hesitate to blast me a lot, and I will answer them as asynchronously as I can. Thanks again for having me remotely. And next year, I will do my best to be there in person. See you all.
Okay, thanks, Joel, for the presentation. So normally all the questions are answered in Discord, so should be okay. So we'll have a little break. We will go back at 1:30 for the presentation of NCC with Carlos, so the computing center in Surf in Netherlands, so to see what they are doing in their computing center. And then we will start the lecture again on GPU at 2. So have a great lunch.
Okay, welcome back. We are here for the GPU week and starting with our dear partner NCC Netherlands for this first presentation of the week. So thank you very much, Carlos, for being here. I leave you the floor and thank you again for partnering with us. It's always great to work with you.
Yeah, it's a pleasure. Thank you very much, Marie. So, hello, everybody. Even though I cannot see you in the camera, I hope that you are seeing the presentation and that you are having a lot of fun in the Grey Scott School. And well, I'm here to present a bit the node of the Netherlands. On our side, as you can see, I am in the office right now. We are actually providing online support because given the number of participants and also the possibilities to coordinate a room, it was considered that it was more efficient to have the online support. So, well, that's why I am here and I cannot show you a room with many people. Apologies for that in that sense, but well, still, I would like to give you a bit of context. Why are we here in the Grey Scott School and why are we supporting this event and how we do actually? So, if I can comment and by a bit introducing myself, so to say, I am from SURF, the institution which is the the tier 1 center in the Netherlands, so the Dutch National Supercomputing Center. I am an HPC advisor, so I do work of supporting users and working with different projects, also evaluating projects for the use of our facilities. And I am also organizer of training activities generally in the Netherlands. I am also the coordinator of the project that is specifically supporting the Grey Scott School, which is EuroCC. EuroCC is the implementation of a project that is having partnerships over 36 countries. So, for example, in France, there is Teratec with the Centre de Competence de France, CC France. And in the Netherlands, it's EuroCC, the same project, with different partners. We are the coordinating partner, SURF. You can see the logo in the upper right corner of this slide. But we also have our other 4 universities that are collaborating with us. In particular, the University of Wageningen, the University of Groningen, the University of Leiden, and the Technical University of Eindhoven. So we are 5 partners in total that we are supporting the work for the EuroCC project, and that are looking forward to having, let's say, a vision for support for high performance computing and advanced computing in the Netherlands. This is something that summarizes our goals in general. We would like to have, so to say, to make accessible HPC and support HPC at all levels of the society, so that everyone in the Netherlands can have a way to access HPC resources and HPC possibilities. So this is a pyramid of how we are located. You can see in this part, in the part of the national clusters, this is where SURF is located. But we have also the tier 2 and tier 3, the central university clusters, and also other department clusters, smaller ones, that are included in what we are forming as the Dutch Scientific Compute Federation. This includes our other partners in the EuroCC project, for example, Wageningen University, University of Groningen, Eindhoven, and Leiden. And we have this type of vision to coordinate from the bottom tiers to the upper tiers, even thinking of the large European projects like the AI Factory and the large European systems, where the Netherlands will have a quota. The Netherlands has a quota indeed, as of now, and LUMI. And in the future, we are also definitely looking forward to our partnership together with France and Greece for the Alice Recoq supercomputer, which will be the second exascale supercomputer in Europe. There are some months until that period, but still, this is our vision. This is the part that we are aiming to support and so to say, the way that from our side, from the Netherlands, are looking at the ecosystem and try to facilitate at best the connection between the different elements, the different partners. In the end, you can think that the Netherlands is a relatively small country, so to say, but still quite densely populated. So it is 18 million people. And 18 million also gives a lot of possibilities and a lot of people having a vibrant, enjoying a vibrant ecosystem. And that's why we need to have a vision that integrates everybody and that is able to facilitate the work on and the access in the end for everybody to computing and storage resources. So well, this is the general idea, and our services as EuroCC Netherlands are aimed at integrating into the existing ecosystem, and since several years we have been optimizing them so that we have provided a way to access to HPC resources and consultancy that was not existing still in the Netherlands. That is specifically for industries and for public administration, so to say. In the Netherlands, SURF has been organizing the regular calls for academic institutions to access compute power since several years, even before the EuroCC project existed. So this is just one part of the ecosystem that is well established and that we count on. But when it comes to, let's say, a researcher that goes into to being an entrepreneur or wants to create let's say, an SME or start monetizing the work, so to say, this researcher should not be just saying, okay, I go out of research and suddenly I have no support at all. I find all the hurdles from the real world, so to say. But instead of that, there are services that EuroCC Netherlands is promoting. So as a starting package, we offer a small proof of concept access to Dutch national facilities, in particular our supercomputer Snellius. Then we have a specialized consultancy, basic support, and even training activities that are open also for researchers, and not just for researchers, but also for SMEs and public administration. So that we think of these new stakeholders as an addition to the ecosystem, and we try to make sure that they are also able to understand the benefits of HPC and working with these activities. So SURF as a host institution is as I commented, the National Supercomputing Center at DR1, and even we have a connection as DR1 Center with for the computations of the Large Hadron Collider for CERN. So many data that is coming from CERN is being processed on our machines, not on our supercomputer, but on dedicated grid facility, so to say. We are also on a national research and education network provider, so we have also the connections for the communications between different research centers in the Netherlands. So that makes of SURF a very large cooperative, and with that, we are providing our services, so to say, just to give a bit of context. And now going a bit more, just to finish, a bit going more onto training. We have a history of supporting training since the times of the PRAISE project, which have been there for several years, starting even as a precursor maybe 25 years ago already, until 2022 that lasted this project. And since then, we have several tasks like continuous evolution and improvement of the training activities. We had also discussions with our universities to improve these activities. And we stayed connected with our European partners. So we have continued with this spirit into EuroCC, and we have tried since 2022, particularly when PRAISE stopped existing, to keep this type of cohesion and make sure that we have a boost for the national ecosystem in terms of training, that we provide training for even for new stakeholders, but also that we are connected with the general European landscape via, for example, projects like the Virtual Academy, the Evita, and also the portal of that I'm going to explain in a moment, or I can show you in a moment. So these are the training activities that we try to offer regularly. We have, in general, work with the systems and also skills courses. So we offer generic supercomputing courses and also the usage of tools that are particularly for VM creation and data management that are available, particularly in the Netherlands, for everyone, but that are a good example of tools that may be useful for almost everyone in, let's say, in every country. So that's our aim, that we provide support for this type of tools, and also for the usage of the systems. And when we think about the systems, we also focus on skills, because using a system and having access to it doesn't solve everything. There are many complex workflows that need to be understood and implemented correctly in an efficient and sustainable way. And that's why we have our parallel programming courses, so that people with knowledge on, so to say, everything that you are knowing in the Grey Scott School at this moment, you have also access in the Netherlands whenever it is needed. Because thinking about that, when we think about training support, a part of supporting this large event, in this case, the Grey Scott School, we are also trying to approach as much as possible the researchers themselves, at least in the Netherlands. And this is why we have organized a series of courses that bring HPC closer to the people, so to say. In coordination with our universities, several of them, like the universities of Amsterdam, University of Amsterdam, Vrije University, and also the universities of Eindhoven, Utrecht, and Maastricht, we are able to deliver training courses on location, not just online or not at SURF, so to say, at our headquarters, but going to the universities, making sure that there is some attendance from the universities themselves and also from the region. So we establish a collaboration so that the universities also can call their SME landscape and everybody that is around in the region to be able to access this course, and make sure that there is some kind of regional interest group that is getting to know about these opportunities and being able to access these courses. So that's a part that we like to promote. So, if anybody would hear about that, and if you are maybe listening to this talk and you are from a university in the Netherlands, you can let us know if you would really like a course in the Netherlands with this type of with the content that I commented at any point, not just a very large course that is online like the Grey Scott School at once, but maybe more regularly spread over the year whenever needed. And that's also including anyone that is online on a different location, because just think that we have a network in EuroCC of 36 countries in Europe, so anybody from any other country in Europe may also benefit from this collaboration. So just let us know. And if you are also in Senegal or any other countries, be also welcome to contact. We can always make some good agreements so that there is a possibility. So never be excluded. Even from our perspective and from my side, I would really hope that let's say, that the HPC knowledge and the way of achieving access to these type of computers should be lower for anybody in the world. we really need to be able to work with these machines and understand the possibilities, even if there may be some limitations of access at some point. The knowledge, at least, should be transferred. So always be welcome in that sense. And maybe just as a last resource and last comment, all that I mentioned, the training activities, including the Grey Scott School, are actually advertised in this portal, HPC portal in Europe, which is a very important reference nowadays. It has become a portal that aggregates several information that is essential for to access resources in Europe and also be able to learn about HPC in a general way. In particular, this is the Service Hub, for example. I just put some screenshots of the portal. It is ideal if you go directly to the portal because then you can see over there well, you can browse, for example, these links in the menu. And a part of the services, so to say, per country, where you can go to services and you can find this map of different countries, here different competencies, and you can select also the country that has the knowledge and just contact these people. So over there, here, this is our node. So this is where you can contact our team in the Netherlands. But here is the node of France for CC-FR, or the node in Germany, the node in Poland, Czechia, many places everywhere that, let's say, in many of the countries in Europe, you can find a node and you can find some support and some person that will be happy to comment about HPC. And also in a general perspective, you have also this type of training baseline that we have created together in the EuroCC project. So if you access and training and then you go to training baseline, you may see this table of different courses that are available. Sometimes you can find links to resources and materials, and in the end, also be able to learn offline whenever it is possible, a part of finding the different courses, the different resources online. Well, this is all that I wanted to tell you. Here is our website, euroccnetherlands.nl. So whenever you have a question, whenever you would like to let us know anything, that's always open. And in the end, we are very happy to contribute to the Grey Scott School in that sense. And just as a very last message, for everybody that is in the Netherlands, please check the chat of the Netherlands because I have posted today morning the offer that even though we don't have the support on site, we would like to offer everyone that is in Amsterdam a visit in the data center so that everyone in the Netherlands has got access to our supercomputer Snellius for the Grey Scott School. So the supercomputer Snellius is actually behind me in somewhere, I mean in the other building, but well, at my back. And we are going to organize a visit to the center. So after the school finishes, either tomorrow or the day after tomorrow, around 6:30, we are going to go to visit the data center and just have a last activity before the end of the day, and hopefully a very nice one also to see the supercomputer live. So anybody in Amsterdam, please take this into account and be welcome to join. And thank you very much, everyone. This has been the presentation. I hope this was just giving you an idea about the project, the support in the Netherlands, and yeah, have a lot of fun in the Grey Scott School. And thank you very much.
Thank you, Carlos. Thank you very much. Well, always very impressed by everything you do at SURF and NCC Netherlands. It was a great presentation, as always, and I would say that our collaboration is really important to us, and we are very happy to share what you're doing with the entire Grey Scott School community. So please feel free to reach out Carlos or ask any question on Discord, as he said. And let's meet in 10 minutes for the afternoon with Pierre Aubert. Thank you, Carlos. See you soon.
Thank you very much. Goodbye, everyone. See you in Discord. Bye.
Okay, hello everybody. So we are back on lecture on the Grayscale School. So I will present to you here the GPU architecture. So how does it work? How we can do with some programming with it, and how to get performances. And after that, we will have some hands-on on how to develop the Grayscale on several versions with the easy way, the not easy way, the really, really complex way, and we will see how far we can get. So if you want to pick the image, normally nothing has changed much, just some fixes, just some typos, this kind of stuff. If you pull the last images, you will be able to follow. I encourage you a lot to pick the image with Obtainer because it's a nightmare to mount the GPU stuff with Podman. So if you get or maybe I can show you to start so you can pull the image during this part. It will be theoretical for, let's say, 1 hour roughly. So if you pick this one, yeah. So here we are in C++17 and my computer is dying, but it's not a problem. And you pick this one, you pull with Obtainer here and you run this one and you will get everything okay. If you manage to mount the GPU well with no problem with the other, it's okay. But today it's not working because why not? So pick the Obtainer, it will be okay. So what's in the GPU? So we have in the architecture, we have memory. We start with memory. So here we will have HBM memory, so fast memory for GPU for computing. Of course, you can have different type of memory depending on what you want to do. Then we have streaming multiprocessors, so they can be called the computing unit in other vendors, but here it's for NVIDIA mainly. And then we have a L2 cache, and we can do some computing with it. So inside the streaming multiprocessor, we will get some cores to compute, as in a CPU. Some part to fetch and decode the data. So remember presentation of Sébastien of Monday. So we have to fetch the instruction and fetch the data to make sure that we can run everything. It's the same idea, but we have one fetch and decode part for a bunch of computing part. So generally we have 2 lines of this in the data sheet. And then we have something to manage the execution, we'll see how does it work, and a shared memory. So that's a really simple description of a GPU. Pretty sure that Joel will say it's a description for tourists, but we can understand a lot of things with that. Of course, one streaming processor is much more like this. So you get a lot of stuff. You get the L1 instruction cache, you get the register file, you get the L0, you get the tensor memory accelerator, texture memory, a lot of stuff. Generally, what we use is, for the classic computing, the CUDA cores, if you want. So this part, so for integer, for floating point 32, 64, we do the classic math here. So once you start a CUDA kernel, normally you are running here, if you create your kernel yourself. But of course, we have tensor cores for matrix multiplication, and they are really, really powerful to do matrix multiplication really fast. It's not that easy to use, so of course, you prefer to express your problem in a matrix multiplication or linear algebra in general, and you use cuBLAS, and everything is nice. So in terms of tensor core, let's say we have a matrix product to perform. So classic matrix product. And then let's bend a bit the matrices, and we can get to something like this. And here, if you have this topology, of course it's not 3D in the die, otherwise it will be a bit too warm. But here, in one place, you say I perform in one goal all my multiplication, all the cross products for the matrices, and then the second one, and do all the reduction, and in 2 steps, you get your full matrix multiplication done. And that's really, really powerful. So to have some examples, if you get tensor core of V100 or A100 for FP16 or FP32, you see that you need to have some computing units. So all the dark blocks here are computing units. So they are not, of course, in 3D, but it's simpler to visualize this way. And since the GPU are evolving, they increase the size of the tensor core, and we need to have much bigger matrices now to multiply, and it keeps increasing. We have extra precision, so TensorFlow 32 for A100, X100. And in terms of performance, here we have the performance of CUDA core, so it's really flexible. You can do everything you want in the CUDA core. You can optimize a lot of stuff. We'll see that also maybe during the hands-on. It will be simpler to do that this way. But for Tensor Core, you have a faster computing. You see it's not totally the same scale from the two sides. Here, 60 teraflop, and here we are 2000 teraflop. So much more. But of course, you have a larger choice of precision, and you can consume less, of course, but you have to express your problem into a matrix product, which is not really easy, but with a lot of design, with a lot of discussion with your colleague, you can manage to do this kind of stuff. The other trick on the Tensor Core is they are really good at multiplying sparse matrices. So if you have a lot of zeros in the sparse matrices, the Tensor Core can determine itself that, okay, I have a zero, so the whole chain and the whole reduction related to this zero can be avoided. And it's really, really efficient. So you can have a speed up of 2 just with sparse matrices. So don't hesitate to use sparse matrices with that. It's really meant for that. So in terms of Tensor Core, if I add the last, yeah?
Yeah, sorry. Do you know which generation Tensor Cores were introduced?
I will show you the whole family after that, but the very first one is Pascal, but it was not as optimized as we have now.
Okay, okay, thank you.
But so yeah, I can develop a bit once I will get there. Good question, really good question. So here we have performances with A100 that you already know, H100 and B100. So of course, everyone is presenting the performances of the SXM version of all the cards because they are really faster. But I prefer to present you the whole family here. So the SXM and the PCI, which are generally a bit smaller with a bit less cores, but they are quite fast, of course. And here you can see, okay, we have an increasing power on the computing on the CUDA cores, but on the Tensor cores, some people are yielding a bit because if you see the float 64 between Hopper and Blackwell, you have a slightly decreasing performance. And that's a trend for the rest here. Of course, it's not really nice for them, but we will see that it's possible to have a loophole for that. So it will be important. So in terms of performance, if I put the performances in a linear scale, of course, we don't really see much float 64. Because of course, before I show you the size, the number of computing units for each precision, but of course you can imagine that if you want to multiply float 64, it takes much place that float 16, of course. So you have less computing unit for the same, for this reason. So in terms of the ecosystem, or maybe I don't have the full, okay, I will show you the full plate after that. Maybe I dropped this slide to be a bit faster, but I will show you the full family after that. So CUDA is an ecosystem. So you know we have the CUDA here, and you can do some kernel development. So with CUDA, with Q++, with QClass, for example. And then on top of that, you have computing libraries. So QBLAST, QLAPACK, QPBLAST, QSCALAPACK, QFFT, QRound, QSPARSE, QTensor, you name it, you have a lot of them. We have thrust also to play with a bit. And IOs, so rapids and cunumerics, legates, and QDF. So we'll see that with the Python part. And under the hood, you have a lot of tricks with IO, so Magnum IO for the parallelism with NVSHMEM, the GPU direct storage and direct network, and direct RDMA with GPU direct, and Nickel for for the distributed computing and for the exchanging some messages as NVC, but not exactly the same tricks here. And then we will also see how to profile, to debug with Insight, because that's really important to at least to know how to profile. To debug, it's not really easy, but now it's much more easier than before. So that's, you recognize all people because they love this tool, because it was so horrible back in the day to debug. You had to think really hard and say, okay, I read my kernel, I know there is a bug. No way to know otherwise. So that's really powerful. So in terms of threads, it's a bit different than the CPU. If I get a CPU, so I have a CPU core. On my CPU core, I can have a thread, and the thread will get the full CPU core, or half is it's hyper-threaded, but still a good big part. If I vectorize, I will be able to use all the vectorized computing which is possible in my course. But of course, the problem is by default, you need to use specific instruction, and by default, it's not vectorized. So that's a bit of a pity if you forget a speed up of 16 or speed up even more if you have the pipelining just because you forget to vectorize. That's not really great. For the GPU, it's a bit different. You have a core, which is really tiny, as I mentioned before, and the streaming multiprocessor is a kind of CPU, but not really. And inside, we have threads, and the thread is pinned to one core. It's living on one core. So the good point is the parallel expression is made by the hardware itself. So you don't have to use specific instruction. You don't have to be bothered with a lot of stuff. You have to, you define a kernel to say, okay, what I'm supposed to do with my element on my kernel, and everything will follow normally quite well. We'll see sometimes it's not that easy, and that's important also to have in mind. So in terms of hierarchy, we'll start from bottom. So we have threads. So the thread will be attached to a core, and it executes the kernel. Okay. On top of that, we have the warp. And the warp is linked to the scheduler of the GPU. And it's roughly 32 threads with all the NVIDIA architecture I know. Of course, it can depend on the vendor, but it's quite, the order of magnitude is quite this one. And you have the guarantee that you have synchronous execution. So two threads belonging to the same warp will be executed at the same time. They will be synchronized. Then we have the block. With the block, we have roughly a multiprocessor, so a match of a multiprocessor. If you program, it's nice to have that in mind. So it's 2 to 4 warp depending on the GPU. Sometimes it's 64 cores, sometimes it's 128, depending on the architecture. Typically, if you have a GPU to do some rendering, you will have more cores. GPU for computing, you will have a bit less. So you have to adapt, of course, depending on what you want to do. And here it's asynchronous. If you have two threads belonging to the same block, you don't have the guarantee they will be executed at the same time. If they belong to the same one, it's okay. If not, no guarantee at all. That's also important to have in mind. On top of that, we have software layers, so clusters, which was introduced for block communication, because of course, if you have Hopper, for example, since CUDA 12, you have 132 streaming processors, and with Ampere you have 108. And of course, the problem is one streaming processor is less than 1/100 of the full GPU. And if you want to stop everyone just to communicate between two blocks, that's a pity. So they introduce the clusters to ensure that, okay, I want to make two blocks communicate, but I don't want to stop my full GPU just for two blocks. Come on. So that's an extra layer, which is a bit hidden, in fact, once you program with kernels. So you have also to have that in mind. And finally, we have the grid. And with the grid, so it's a full GPU, generally, and you get Hopper, so you get 8,000 cores, 7,000 cores for Ampere, depending of the, and 10,000 for Blackwell, if you want to have also the information. So you have to deal with a lot of cores at the same time. So in terms of execution, I have a thread, but of course, one thread makes no sense. So I have a warp instead, because the warp makes sense. If I have some instruction, they will be loaded 2 by 2, and then they will be executed also 2 by 2. So you have the guarantee that you can execute everyone at the same time. But what happens when you have a condition? If you have a question, no?
Could you clarify? I didn't quite catch the cluster. Could you clarify the difference between cluster and grid? Like
cluster is
it enables faster communication between.
Yeah, if you need to have communication between blocks, you use the cluster to be sure that you have few blocks and they can communicate together, but without having to stop the full GPU just to communicate for these few blocks. That was the case before CUDA 12. And since a block is really small compared to a full GPU, they introduced that to make sure that if you want to compute and to have a faster communication, you don't stop the full GPU just to communicate a bit.
So when you want to communicate between two blocks pre-clusters, you had to stop the full. You need to stop the full GPU.
Yeah, if you don't have the cluster, yeah.
Okay, thank you.
So you synchronize everyone. You say, okay, I want these two to communicate, or some others, but you can have several clusters, independent and asynchronous, and it's much faster, of course, to do that. So that's why they introduce the concept of clusters. So once you have a condition, what happened? We saw this weekend that sometimes with glasses, okay, but once you have a branching predicator, it could be a bit annoying. What's happened with the GPU with that? So first, we will load the condition, and everyone will compute the condition, of course, to see if it's true or false. Then we'll have those for which the condition is true. They will execute the then statement, and the other will wait politely, because threads are really polite together. And then once it's done, the other will execute the else statement, and the previous one will wait politely, because threads are really polite together. That's why, generally, once you program with a kernel, everyone is telling you, don't put condition in your kernel, because you will always pay to the two statements in the if. You will pay the then and the else statement. Even if you have only one thread which disagree, if you want, compared to the other, you will wait for everyone. So if it's a tail problem, it's not a big of a deal. If it's often, we'll have a problem of performances. Yeah?
Condition, do you mean predicate or such as an if statement? Because you have predicates, right?
If test, really an if statement, yeah.
Okay. But this does not apply for predicates.
You mean?
So you can have execute add the register 1, register 2, output to register 3, only if condition this holds. So you have different predicate registers in the GPU. But this is only for like branching, not for, okay.
Yeah. So in terms of mapping, so we have a lot of cores. We cannot move them because they are in the hardware. So the goal is to make sure that you map your data on top of your cores. And then you can pass through everyone at the same time and do the computing at once. And that's really important, and we will see in the hands-on that if you don't have that, you will kill your performances. So you map data on the threads, and you need to make sure that, of course, you read the threads and the data in the right order. That's important. So for the data and thread mapping, you have some tricks in the kernel. So we have the thread. The thread is attached to a core. We have the blocks, and the blocks are attached with a streaming processor. It's a nice way to have that in mind. And then we have the grid, and the grid is a full CPU. We will forget the communication part for now. It's really simple. In Grayscott, we don't have communication, so really simple stuff. At least for this year, we don't have communication. And then, so we have the thread ID and the block ID to refer to which ID, which block, which thread in which block. And since things could be a bit complex, we have three dimensions for the ID. And of course, you have some limitation. You cannot put all the size you want. You have a maximum number of threads per block. You have a maximum number of threads per X, per Y, and per Z. So you have to deal with that and make everyone fit nicely into the GPU. A question on Discord. If I get here. Umar has a question. Hello, Pia. Is it possible to have a CPU core that can run more than 2 threads? Yes, if you have hyperthreading. But it was a question for last week. Albin said, I think it's very much possible. I don't think vendor implement that because it would be slower. Yeah, as Sebastian said, you have to remember that if you have one thread doing some I/O, one thread doing some computing, things could be quite nice. If one thread is getting all the bandwidth, it will kill the performance of the other. So you have to make sure that they will live nicely together if you want to do some hyperthreading. Otherwise, you will have a problem. So, block size. How do I determine my block size? Because of course I put some thread in the block, but at some point it has to match. So how do I do? So let's pretend that we have an Andamar product to perform, because of course it is Grayscott School, but it's one of my presentations, so there is an Andamar product. We have 1,000 elements to compute, and we can have several strategies. We can say, okay, let's have the first scenario, let's do 10 blocks of 100 elements each, just to see what's going on. If we do that, all the blocks are, of course, determined with warps, because thread alone makes no sense. So we have this kind of blocks. They are all the same. It's nice to see what's going on, but they are not really well used. And here, we have a usage of 78%. Okay. Let's try to have another strategy. If we say, okay, let's change a bit. Let's say, okay, I have only 8 blocks, but of size 128. What's going on? If I do that, I have 7 blocks which are the same, so really well filled with threads, no problem. And the last one is a bit less efficient, of course, because I don't have a power of 2 element here, or a multiple of 32 elements, I should say. So here, it's not really efficient for the last one, but globally, I use 98% of my GPU. So the occupancy, if you want, of the GPU. So you can have a padding, you can have a if statement just at the end, because here, everyone will be really fast. And this one, we have the 2 statements, but not the other. And if the else statement is just say do nothing, it's not a problem. So you can do boundary, but not if cascade in your kernel, never. So in terms of read and write, how does it work? So we have one sector is 32 bytes, so it's the same idea of the sector that we have on the CPU. And of course, as Sebastian mentioned, once you get some data, you don't get data byte per byte, it will be way too slower, so you get a bunch of data and hopefully we'll use everyone. So if I have a cache line on 128 bytes, so 4 sectors, for example, I can say, okay, I want to read or to write a 4-byte element with my 32 threads. What's going on? So if I do that, I will access 4 sectors. So contiguous data, contiguous access, everything will be nice. Normally, should remind you the vectorization. That's quite the same stuff. Even if it's not declared the same way, but that's the same stuff at the end of the day. If you want to read 8-byte elements, Not the same. You have contiguous access. So that's really flexible compared to having one vector register, one other vector register. Here you declare what you want to do. You have contiguous access, it's okay. So really close to CPU vectorization. That's why, of course, if you have a code on CPU and you want to port it on GPU, generally, if you improve it a lot to make sure that it fits on the GPU, you will have a speed up also on the CPU. Because you have better vectorization, better prefetch, better data format, this kind of stuff. So the memory layout matters. So if I take my sectors of 32 bytes, and I have my structure of coefficient of 80 bytes, for example, if I do an array of structure, I will get this in memory. For example, in red, you will have the 80 bytes of my struct. And the same for the CPU. If I read U, I will jump from sector to sector. And here you see in the slide, I cannot get much after the 5th or maybe 6th thread, and it will be really, really too long to have this in the slide. So I use only 4 bytes when I fetch 32, and I kill my performances even on a GPU. The GPU is not magic. That's the same principle. But of course, if you say, okay, I don't want to have an array of structure, I don't want a structure of array, so I create my same coefficient, but with the trick Joel showed this morning also, you can split everything and you have a lot of tensor, a lot of vector instead of having one structure of coefficient. You will get this kind of stuff in memory, and of course, I get back to the previous slide and I read everyone at the same time with for contiguous access in sectors, and it's really, really fast. As fast as the hardware is supposed to be. So that's a good point. Here, I load everyone I used. Nice. The same for the CPU again. So the question we have to ask, we have a lot of cores on the GPU. So how many threads do I need to launch on my GPU? Do you have an idea? If I have 6,000 threads, A100, how much thread I am supposed to launch on it? More or less? A bit more? No idea? To use my GPU at its full potential. So I have 6,000 threads, 6,000 cores, sorry. How many threads do I need to launch on my GPU to be sure that I use it properly? You can have any data you want, just a number of threads.
You have like 100 SMs, and then you have like, is it like 1,000 threads per SM? No, that can be the case. But isn't it like 10,000 approximately threads per GPU you have?
You are not really close, but that's a good starting point. Or maybe if you have another idea, yeah?
My impression was that you just need one CPU thread. I'm not sure.
One-to-one?
No, one CPU thread for.
You have one CPU
Streaming
thread
the
to
data
manage
to
your
the
GPU, but inside your GPU, once you create your kernel, how many threads do you want to start? Okay, I will show you. So we have the Grayscott, and here on the x-axis, I change the number of threads. I start on my GPU, and on the y-axis, I measure the total time in seconds of the computing for the same problem, the HD, the classic HD computing that you already know. And you see that you have to start a lot of threads. And if I pick, for example, the classic way, because on the CPU, you have 32 cores. You start 32 threads, maybe one more for the I/O, maybe two more if it's a big machine. It's okay. And here, if I pick 100, for example, here, I get my 10,000, okay, it's 6, but it didn't fit with my program, so I put 12,000 instead of 6. Okay, factor 2. I'm here in terms of performances. If I start a lot more, 700,000, I'm here. And from here to here, it's a speed up of 41x. So you don't want to start roughly the same number of threads than the number of cores. You want to start much more. Because the trick is on the GPU, you will have the warp and you will have a lot of warp on the fly at the same time. For example, on a Hopper, you will have 64 warps on fly at the same time on one streaming processor. That's why the beginning of your of the reasoning, which was really good, but you have a lot of things on the fly. Yeah.
So if you suppose that you use all of your streaming multiprocessors, but you when you increase the number of threads per streaming processor, you also reduce the number of registers that's available to the thread.
Yeah.
What is your experience when it comes to weighing the amount of registers to the amount of threads available per streaming multiprocessor?
Yeah, we will practice that in the hands-on session after the lecture. Basically, what you want to do is to have a block nicely defined. And if you need to start more threads, you create more blocks and you let the block as it is. We'll do that just after the lecture. And it's really, really efficient. That's the strategy of NV Fortran, that's the strategy of NVC++, and that will be our strategy because I will show you how to sneak peek the nice ideas of the compilers with Insight. So that's important, yeah, good question. So again, express parallelism, especially on the GPU, you want to express parallelism because you want to have a lot of threads running on independent data, independent stuff. It's important. So if you have an element and you are lucky because you have a lot of independent elements, you can express parallelism. And if I have a particle, for example, as Joel this morning, I can say, okay, I have a position, for example, X, Y, and Z for my particle. And of course, I want to separate these values because at some point, I will have to mix them. Maybe there is a cross product to perform, maybe there is some dot product to perform, some reflection, this kind of stuff. And if I have all these values contiguous in memory, I cannot. So I have to split everyone to be sure that I can mix tables nicely. So I can have this kind of table. I can do the same for the velocity. I can do the same for the acceleration. And here the question is, okay, I pass through everyone. I compute one particle, the evolution of one particle. And here you have to ask yourself, okay, is it bad if I get the results of the 19th particles before the other one? If the answer is no, you can say, hey, maybe I can pass through 8 of them at the same time and vectorize. And you can say, oh, maybe I can pass through all of them at the same time and GPUify, because you want all the particles to be updated at the end of the call, but you don't care about the order. At the end, if you get everyone updated, it's okay. So that's also important, and that leads to another problem. Sometimes you have events, so independent event because we are lucky, but maybe they are a bit too big and they don't fit much in your memory. Maybe you can put, for example, if I take the analysis I'm working on, I can put 6,000 elements on one GPU, on my laptop, for example, for computing, because they are a bit big. As I said before, 6,000 threads is not enough for 100 or this kind of stuff. So I have to break down my event into pixels, for example, into captors, into cells, into whatever you want to call them. And maybe it's still not enough. And maybe you want to split again that into slices, pulses, waveforms, time response, and this kind of stuff on your pixels. And then I have a big tensor and I can play with it, and I have to ask myself, okay, what is the ordering of the storage for my big tensor? And for that, we have to ask ourselves, okay, what do we want to do with the tensor? So let's pretend the first step is calibration. So I get some voltages, and finally I get some photons, some energy on my captors, for example. Let's pretend also that calibration does not care about the ordering. So you have the best performances, whatever the ordering of your data are. Could be possible if it's a scalar, for example. Okay, let's get the second one. The second one, you can have an integration. So integration means reduction. Reduction means sum, and sum means back dependency, as we saw last week. So I don't want in memory to have this element contiguous to this element here, because I will sum them at some point. So they should not be contiguous in memory. So if I do that, the contiguous data are on this axis. So it could be the last one on C++ with row-wise, or could be the first one on Fortran in column-wise. You get your, you can do it as you want. Let's pretend in C++. Then, if I determine this axis, I can say, okay, I want to sum this line to this line. So I don't want this line to be too far in memory from this one. So obviously, the second axis with vectorization, the second axis will be this one. And finally, of course, I have the first axis here will be the event. And on the event, I can parallelize on cores, on node, or cluster, or everything I want, no problem. Everything is slightly nice split. So again, computing drives data storage. You cannot store your data and hope for the best. You have to think before, okay, what do I want to do with my data? What are the steps of the analysis I want to perform, or the simulation I want to perform, and then you order your data to fit these needs. Otherwise, you will have some problem in performance. Question on Discord, okay. Thanks, Albin. Also, Omar said, thanks, Albin. I've never yet seen a multi-threading that exceeds 2. Neither do I. Not sure it's possible to have more than 2. Maybe we have to ask Joel. Don't know if there is something more than 2. 2, it's okay. More than 2, I don't know. So I also as many as we need to cover the input space for what? Okay, question from Stevenson. Is there a work stealing mechanism used when there are too many threads? Depends. If you are using NVC++, normally you don't have too many threads. If you start too many threads, your GPU will complain a bit and say to you, no. You have a limit, you have a really high limit. So if you get to the limit, I'm not really sure what's going on, but normally your GPU will just reject your kernel and say, no, it's too much. You exceed the size, the maximum number of threads per block, the maximum of number of threads per x-axis or whatever, and your kernel will not work. So it's better to, as I said before, it's better to have more blocks, nicely defined blocks, but more blocks. A question of Abdul: how one could compute the number of possible parallelisms one can have? I ever thought the number of threads is an integer multiplication of number of maximum possible parallelisms we use at the hardware. It seems different. You're saying there is different loading execution cycle inside the GPU. Yeah, it's a bit different because, okay, I did not want to enter in the detail, but you asked for it. So the thing is, decoding and fetching instruction on the GPU takes a long time. So you don't want to execute one warp at a time per streaming processor. So typically, that I said just before, on a hopper, you will have 64 of them in flight at the same time. So remember the CPU pipelining, you have the same for the warp, roughly, on GPU. So warp which are getting to be executed, warp which are executing, and warp which were executed, and we go back on the stack. So you have a stack of all the warps which can possibly be executed by the block, by the stream processor, and then the SM will pick one warp to send to the execution, and each time you have a lot of warp on the flight, so you cannot send them. Warp which are available because you don't wait for data, for input, for whatever stuff. So it's you jungle, in fact, with a lot of warp. It's not I put a warp and execute it. It's just you jungle, and the time you launch a warp, it's a time once you have a lot of warp which can be executed at the same time. So you have to fill the GPU with a lot of work to fill up this gap, to be sure that you constantly running and constantly starting some computing, even if there is only one part of the computing, but you have to send to the computing and then to fall back, and you continue to jungle with that. That's a circus, in fact. That's a computing circus. So Alessandro said the execution cycle in the CPU is very similar to the CPU. Yeah, except this decoding stuff, which is really heavy compared to the CPU. But yes, the difference that is the CPU has much simpler execution to the CPU. Yes and no, it depends. If you speak about branching predicator, yes, there is no branching predicator in the GPU because we load everyone and we figure out if it's had to be executed or not. So there is no guess. But otherwise, you have this jungling stuff, which is not really simple to have. Furthermore, the GPU is a really fast mechanism to switch the warp currently in execution. Fast depending on what you are talking. Compared to a CPU, it's not that fast. But yeah, not on modern GPU at least. CPU has hundreds of cycles to change a thread during execution. Whenever you perform a warp swap on the GPU, we spend a couple of cycles on such an operation. Yeah, but you have to have a lot of warp running at the same time. Otherwise, you underuse your GPU, and you don't want to do that. So question from Rito Brata. If you have time, can you please describe some case studies where theoretical occupancy doesn't match actual usage, 98% theoretical, 75%. We will do that in the hands-on with Annecy, because Annecy can determine the occupancy of your kernel. That's really important and really powerful. I'm pretty sure I will be late with all these questions, but never mind. We'll do that after the break, so we'll have plenty of time to play with that. No worries. Everything will be under control, maybe. So, and let's start with Adama product in CUDA. And then we will have a higher level of abstraction. So CUDA, element-wise operation, really simple. I can create my kernel here, so you recognize the global statement to say to CUDA, okay, I want this to be executed on the device or on the host, depending on what you want to do today. Okay, no problem. Then you have the thread position. So it's really simple, one dimension, because otherwise it could get really heavy to compute. Let's start simpler. And then I have to start my kernel, to launch my kernel. And if I do that, I need to allocate some stuff on the GPU. Since I allocate some stuff, quickly I deallocate some stuff just to be sure that I don't forget to free everything on the GPU. If you call this kernel a lot of time, maybe you want this to be outside of this call to be sure that you don't reallocate much at the same time, because of course, think about Sébastien on your shoulder saying you that allocation takes a lot of time, so please remove the allocation from the call and do the memory parts, ideally the first place at the last place and nothing in between. So you will use your memory much more efficiently. Then we have to transfer data onto the GPU. So we get your Y and X tables and we put them on the GPU. So we can do it explicitly with the CUDA mem copy here. And then we have to transfer the result back. So CUDA mem copy device to host, and here CUDA mem copy host to device. Then we determine the block size. So it's a really cranky way to determine the block size. We can have a much more advanced way to do that, but it's in the lecture if you want to have the detail. I don't have time here except if you have questions, but I don't have time here. So really simple, one dimension is really simple. If you start to have 2, 3 dimensions, it's a nightmare to do efficiently. So that's why I use NVC++ most of the time to see what's going on. And finally, we call the kernel with the triple bracket that you might know. So I create my grid, my block, and then I have the triple bracket. I put them here, and I put my parameters, and it's okay. Just started the kernel. So I get everything at once. So it's not that horrible, but you have to pass through it to understand what's going on, and have the right reflexes to be sure that everything is nice. So once you time a bit your Adama product in CUDA, you will get this one. So here in purple, I have the full time with the data transfer and the allocation. And here I have only the time of the kernel. So you see that, of course, transfer costs a lot. And the point is, once you ask the NVR server settings, for example, or for the usage of your GPU, you will have 100% here. Okay, fair. Here you will get 98%. Okay, not so bad. Here you will get 60%. And things start to be a bit annoying because here, in fact, it's not 60%. You need also to remember that Shannon-Nyquist theorem that if you don't have any sampling, you lose some data, and here the sampler maybe is not fast enough, and you are not at 60%. But the profiler, the sampler, thinks you are in 60%, but it's not the case. You are less. Use less the GPU as this. And then 22, but it's not 22, it's maybe 10 or 5%. So always criticize the results you get from a profiler or from the system monitor, for example. If it's 100%, good chance to be 100%. If it's less than that, maybe it's a bit optimistic and you are not really where you are supposed to be. So be careful about that. It's important. So let's do the same with thrust, with our Adama product with thrust. So element-wise operation, we can do that. Much more compact with thrust. So here I allocate, initialize my host vector. So it's a std vector, but for the host. Then I transfer host to device. So the trick is really, really nice. You have a device vector and you create an equal here with a host vector, and you have the transfer automatically. Really has to have this kind of stuff. And by the way, I didn't speak about the naming convention, but yeah, it's quite nice to have D stuff and H stuff to see which one is on the host, which one is on the device, because you don't want to mess everyone with everyone else. The same for the pointer you pass to a kernel. It's nice to have this naming convention to see, to not mix things up. Then transform, which is really close to std transform. So you compute the Adama product, you pass a lambda, so a bit special lambda because you need to pass host and device decorator to this lambda to tell thrust that, okay, you can use this lambda on the host or on the device. It's okay, no problem. It's working well. And then you can create your product here. So here the good point is you don't have to worry about the size of the warp, the size of the block, of the grid, of everything, the dimensionality, this kind of stuff. you just create your lambda and Thrust will figure out what to do. It's also a good point if you don't really know which size of a block to determine, this kind of stuff. You do a small example with the same data as you are supposed to do, and you see what is the strategy of Thrust. It's nice to get sometimes. Then I transfer the device, the data device to host. So here I'm my D vecraise in my H vecraise, and I finally print the result. So you get the full example here with the includes, because it's important also to have the includes. And if you compile that with NVC++, it's okay. Everything is okay. So here we talked about NVCC, CUDA, and Thrust. But since 2020, we can do some black magics with NVC++, and it's really powerful, and of course I have to show you. So here, you can say, okay, if I use C++17 with std_par equals GPU, my std transform, std for each and stuff can run directly on the GPU. And Vincent will show you a bit later how to do the same in Fortran, and that's really, really powerful. So if I take my Adama product again, I have my element-wise operation here. I can say, okay, let's do a classic C++ loop, or C loop if you want, even more like a C++ loop. Okay, I don't really care of the ordering, because if I compute, as I said before, if my 19th element is computed before the first one, I don't care. I need to have all the elements computed at the end of this function. Okay, so we can use std transform. And nobody uses std transform because it's not really nice to handle, and what's the point? But now we have C++17, and in the std transform, we have an execution policy, which is really important here. So I can tell to the compiler, okay, let's do a sequential operation. Let's do a non-sequential operation, so vectorize, unorder, everything inside it. Parallel execution or parallel and non-sequential operation. And you want to use parensec. If you have, maybe I should say that also, if you have recent GPU, so A100, V100 up to now, you have to use parensec to make it work. If you have older GPU, for example, Pascal, this kind of stuff, you need to use par. Parensec does not work. Because why not? I don't know why, but it's the case. So I have some trick. I'm pretty sure most of you will have some more recent GPU, so parensec it's okay. In the past, if you use older GPU, you can have some trouble with the parensec. And the funny part is when I say it's not working. It's just if you use parensec on an old GPU, the GPU will say no, I want par. But if you use par on a recent GPU, it will compile, it will run, and after 2 hours, it will say, the computing should be 1 second. And once you profile with Insight, it will say, oh, you have 1 thread running on your GPU. That's a pity. So use parensec for the GPU. It's important. So once you have another product like this, or everything you want to do with some magic, some std magic, you can have CMake with C++, CXX, and CC, so to get your C compiler and your NVC++ compiler, and everything will be okay. So CMake will pick the NVC++ compiler as a C++ compiler, and everything will work. For Thrust, it's the same, and for std transform, it's the same. If you use NVC++ std_par equals CPU, everything will work, and as all the compilers, NVC++ will use TBB, threading building blocks, which is a parallel library of Intel. If you use G++, we will use TBB as well, and Clang will use TBB as well. And it's really funny, because if you do some performance tests, you get exactly the same performances, because under the hood is the same library, compiled with the same options. So that's really fun. They agree on this kind of stuff. The trick is you need to explicitly link to TBB because the compiler does not know where you install TBB on your system. So you have to tell the compiler, okay, TBB is here. Get TBB here. Yeah. Threading building blocks, it's a parallel library of Intel. So every time you use some fancy stuff, std transform, std reduce, std for each, with the CPU computing, with a par unsec, unsec execution, TBB will be called under hood for all the compiler I mentioned. So if you they agree on this backend. And for the GPU, it's the same. So you have NVC++ std par equals GPU. So it's working with Rust under the hood. I will show you that just after. And the important point here, do not link explicitly to CUDA. Otherwise, you will have an error. Don't help NVC++. NVC++ will figure out automatically where to link, to which one to link. But yeah, that's a bit of a trick. If you use TBB, you have to explicitly link. But if you use GPU stuff, do nothing. Otherwise, it will link, but you will have a crash on the execution. That's a bit bad also. So avoid static allocation also. NVC++ wants to have a perfect match on all the pointers you have on the CPU and all the pointers you have on the GPU. If you have static allocation for a 3x3 stencil kernel, for example, you will have CUDA error, CUDA memory error on the runtime. So every time you have this kind of error, think, okay, maybe I forgot a static allocation somewhere. And you will see that if you want to use HDF5, somewhere means everywhere. And so you have to avoid compiling HDF5 with NVC++, otherwise you will have a problem. So do a library nicely on the side, and everything will be nice, and use it only on the CPU. And for the GPU wizardry, you can use NVC++ only for the computing. So that's also a great way to improve your design. You are forced to do that, otherwise it's not working. So that's a good point also. So in terms of memory management, we can do a lot of stuff. We have the classic way I already showed you. So you have some stuff in a RAM on the CPU, and then you transfer explicitly your data on the GPU, and then you can use them on the GPU. And of course, like everyone, sometimes we forget to do the transfer and we have a CUDA error. And the CUDA will tell us, don't have the data. Okay. Since 2020, November 2020, we have the unified memory. So unified memory in terms of software, not in terms of hardware as we get a bit after. So here, if I get the data on my RAM and I try to access it on a GPU, I will have an error, but drivers catch the error and say, okay, I will do the transfer for you, don't worry, no problem, it's okay. So you still have an error, but the error is handled by the driver itself. You can do some wizardry, we'll see that also in the hands-on in more detail. So if you do a profiling with insight of the Adama product, you will have this kind of stuff for a big Adama product. And here, if I zoom, you will recognize that, okay, we have page fault, H2D, so host to device, transfer. So I have my error I mentioned just before, and then I have a speculative prefetch. So the driver will say, okay, you tried to access this data, I will give you these and should be okay. And just after, okay, not enough, okay, let's pick another block and so forth, and so on and so forth. So here you recognize trust, because of course under the hood, when you do some trick with std transform, it's a trust transform with cube, which is called. So you have all the stack here, so you can see what's going on precisely. And of course, that's okay for triadic. So for x plus y, this kind of stuff, not much. But if I want to do x plus y times z, It's not triadic. So in C++, it's really simple to do. I had a table in my loop. If my operating system is not annoying, it should be quite okay with the page. And in C++ 17, you can have a trick. You can use a vector of index. It's not really elegant. It's not efficient on CPU, but on GPU, it's really nice. So we can do this kind of stuff. We have to pass the std vector by copy. That's really important for it to work on GPU. So it works well on GPU. You need an extra table. It's not really elegant because you have a table of index, basically. So, okay, not that good, but quite efficient. And it's really close to CUDA kernel. So if you have the habit already to program CUDA kernel and you want to do this kind of stuff, okay, I have an integer. My integer is my position of my kernel is inside of the whole computing I want to do. I'm not lost. Okay, I have one dimension, but I can figure out how to manage that if I have only one dimension. So quite nice, but you have a big table of index. That's a bit of a pity. So if I do some thrust triadic here, so I have a type iterator tuple, so you can do some magics with thrust. So there is a zip iterator, so you can do it in thrust. Not in STD right now because C++20 is a bit. You can use it, but sometimes it's not working, depending on the compiler and depending on what you use in C++20. But for C++17, it's okay. You have a zip iterator, everything is working. Then you can call your thrust transform as before. You get all the information. You can open your tuple, and it's okay, no problem. We can do it in a more C++23-ish way. So for example, if I pick a Cartesian product, so I can say, okay, I have one array of n and m and one array of m and n, for example. I can say, okay, I want to have the Cartesian product between the two, to have all the possibility, all the tuple between the two. And I can do this kind of stuff. I unpack my index. So here it's really close to a really kernel programming. So I have several dimensions because, of course, if you are dealing with matrices, having several dimensions directly and not one to be bothered with the size of the matrices. If they don't have the same size, it's annoying. You have to get back to the indexes and then to re-get back to the position inside the kernel. That's really annoying. So here it's nice. Normally there is no index allocation by this, but I never figured out how to make it work. So, but theoretically, it's really nice. So it's nice for broadcasting, but if you want to broadcast, you can do better. So basically, if I have A times B, but B is smaller, but a multiple of A in terms of size, we can do that. We can do join here with a repeat. So basically, you have the vec B in terms of iterator, and then you repeat till until the end, and then you join to be sure that you don't have a repeat slice together with a repeat as a vector of vector, for example, but a repeat instead of one single vector, which is really nice. And then you can use your execution policy, and you can execute the same on the two, because at the end, the extend vec B will have not the same size, but since we cut at the on the end of the A, we will repeat until we reach the end of A, so it's okay. So it's not vectorized yet. So we have to wait a bit for the future, not yet, but it's on the way. It's on the way, but that's really tough to make it work, of course, because here I speak about join and repeat, but people of the C++ standardization committee wants to make sure that it works with all the combination of all the other stuff, so the 150, 200 STD stuff that we can have. So because I mentioned every time the for-each, the transform, this kind of stuff, but you have lots of kernels, 150, something like that. So it's not really difficult to make it work with all the kernels and to make it work efficiently with all the kernels, so we have to wait a bit still. So it's not parallelized yet also for, in fact, because of the repeat for now. So the repeat is preventing everyone to parallelize for now at least. And since G++13, it's possible to compile, which is really great compared to before, because before it was not even possible to compile this kind of stuff. Now it's possible to compile, but we don't get best performances right now, but it will come at some point, of course. So we can do some extra magic with CUDA graph. So classically, once you have a kernel, so I want to start kernel 1, B, C, D, etc. I will start the first kernel. So I'm on the CPU, I start the first kernel, I'm fall back on the CPU, I'll start the second kernel, etc., etc., etc. And it takes a time. To start a kernel, you have a certain time. As once you call a function, you have a certain time just to jump in the memory where the function is and to do some stuff. Here's the same. You start a kernel, you have to wait for the GPU to say, hey, okay, it's okay, I get your kernel, and then you have to wait for the end of the kernel, etc., etc. If you have small kernel, it's a nightmare because you will wait for the starting of the kernel, you'll launch of your kernel, and of course you want to have small kernel because for flexibility, for design, it's really nice, but you kill your performance if you do that, and you don't want a big kernel because it's bad in terms of maintainability. So let's try to have a graph, and the idea here is to say, okay, I have a graph, I create my graph, I start my graph, I wait for the full graph to stop, and then I fall back on my CPU. And if you have a lot of small kernel, that's really, really efficient. And we do have small kernels. So that's a good point also for the Great Scott reaction. So every time you have small kernel, think about graphs, and then you will see how to program them. You will have a heart attack. I prefer to warn you, but at least you know that they exist. So if you have a graph or kernel here, for example, you can say, hey, maybe if I execute my graph like this, I can execute B and C at the same time and D and E at the same time. The trick here is you always have to remind you that it's a parallelism by opportunity. You don't say, writing this graph, I won't be executed at the same time of C. You say it's possible. But if B uses too much threads or too much blocks, or for example, and C cannot fit in the GPU at the same time, it will wait. And you cannot see that. Otherwise, if you say, okay, the computing is too long, or you watch with Insight and you see the kernel are not overlapping, you say, maybe there is a problem. Maybe B or C cannot fit together. So that's opportunity. And if someone is a bit late to the other, maybe it will not arrive during the execution process. So again, you have to check. So you can express more parallelism, which is really nice because sometimes, as I said, you want to break down your data to be able to start a lot of threads, but maybe it's not possible. And maybe you want to do another thing at the same time. So you can have this kind of flexibility with that. So there was some update 2 years ago about that. So the problem is here I have an iterative execution. So I want to decompose, I don't know, Krylov, QR, whatever algorithm you want. And the problem is, okay, I start my graph, I compute my graph, I fall back on the CPU. Do I need an extra iteration? No. Okay, yes. Okay. I start again my graph. I do another iteration, etc., etc. That's annoying. And of course, you pay the price every time to fall back on the CPU. And you don't want that for an iterative algorithm. And I'm pretty sure you all have iterative algorithm you dream to put on a GPU like this. Not anymore. Now you can say, hey, I put a while inside my graph. I can. It's possible. So I iterate directly on the GPU, and once I converge, I stop. If you have an infinite loop, you have a problem. But if you don't have an infinite loop, it's okay. So that's open doors. So that's a nightmare to debug. If you don't have inside, if you have inside, it's okay. Nice to have in mind also. Question on Discord? Okay, question on Discord. Okay, question on Discord. Question from Bastien. Hello, don't really get the point of having unified memory in terms of performance. I understand the CPU RAM has bandwidth improvement, but at the cost of lower GPU RAM bandwidth. No, there is something more. Yes, if it's unified memory in terms of software, and I will show you maybe for the hands-on with Insight, the laziness has a price to pay. So the driver will try to automatically put data on the GPU regarding that's what you are doing with your kernel. But if you have a lot of amount of data to put on your GPU, if you put it directly, explicitly, it will be much more efficient. For small data, it's okay. For bigger data, it's better to do it explicitly. So yeah. We will practice that in a hands-on maybe after the break, because otherwise it will be a bit too short. So in terms of updates, there is more in the graph, because here I have my full graph with a while loop inside the graph and can iterate on my GPU. It's nice, but I can have a condition. Can have a condition node, and I can express another graph inside the node of a graph. I can put another graph inside my condition, and maybe I have an extra graph with another loop for another scenario, whatever I want to have in my GPU. It's totally possible. And the good point also with this way of doing things is you can reuse kernels. You attach a kernel into a node, you use a node several times, it's okay. You can do that. You can do this kind of wizardry. It's totally possible. And there is more, because if you use QFFT, Nickel, NVC, etc., they all are compatible with graphs. So if you call a FFT inside the kernel or whatever you want, there will be a node inside the kernel and inside the graph, and then you can start to say, okay, I want to call my kernel, I want to do an FFT, I want to do everything. Everything will roll automatically, nicely with the graph. So you have several modes for the graph. We can have that later in the hands-on if you are interested in. So plenty of stuff to show you. So feel free to ask if you want to move in another direction. Normally should be okay. And since CUDA 12.4, you can do that. So normally no more excuse. I'm pretty sure you all have CUDA 12.4 now. So you can already play with that, no problem. So in terms of floating point computing, yeah, it's okay. We'll do some magics here. So as Vincent explained to you, with a float32, for example, we have a sign. So -1 times the sign. We have a mantissa, we have an exponent, and generally we can do some math with it. So if I have A and B, and I want to do an operation between A and B, addition, for example, exponent of B has to match the exponent of A. So I want to do some trick. I want to push a bit, change a bit the exponent of B to match the exponent of A. But at some point, by doing that, I can lose some precision because I don't have an infinite mantissa. At some point, maybe, if not well conditioned, I will have a problem. But now, I can perform my operation. It's okay. So, oh, the full family is here. Why not? That's a cameo of the full family. So here for the tensor core, okay, a strange thing happened. So here you get Turing. So the very first one was, the very first one is Turing. Then you have 100. So Volta, Ampere, Hopper, and Blackwell. They don't fit in the slide, so I don't put Blackwell. So to have the detail, in Turing you don't have the full cross product done at one time. It was not possible yet. So here you have a mix between vectorized computing for the first matrix and scalar computing for the second. So you don't do the full cross for the two. You just say, okay, I take one line of the first, one scalar of the second. So you have much more steps to do the same computing. That's why even if you can have slices same size, a bit more here for Volta, but Volta is much more faster than Turing because Volta is one step. So here it's really fast. Here's the very first one with Tensor Core. So that's a bit more difficult to have performances. But here you see that for Hopper, for example, or for even Ampere, you need to have big matrices to use efficiently your Tensor Cores. So if you have small matrices, put them together, do something, because otherwise you will not use as your GPU as efficient as possible. So there is a lot of trick to be involved here to be sure that you are efficient. So Tensor Core is really good and really big, and we can do a lot of stuff with them. But let's try to do some mathematics. So let's emulate float 32 computation with brain float 16, because there is no float 32 on CUDA cores. It's TensorFloat 32, and TensorFloat 32 is the float 19, and float 19 is not sexy, so they said TensorFloat 32. That's a question of marketing. So let's multiply polynomials. Yeah, for the 10 last minutes of the lecture. So we have A and B. So we have coefficient K and coefficient A, so or B. So you can see X and Y if you want, this kind of stuff for the polynomial. If I multiply the polynomial, I get this horrible expression. So basically, if I rephrase that in nice schema, I get my A times B here, and I get this tensor product or cross product if you want. So I get my matrix of coefficient also, and I can do the same here, and then I do a dot product between the two, and I finally get my result. Okay, that's a loophole for what? Let's try to decompose brain floats with brain floats. So I have two floats, and I decompose one float in 3 brain floats 16. And I get some coefficient, A0, 1, 2, and B0, 1, 2, and I get some coefficient K here fixed, 2 power 0, 2 power minus 8, 2 power minus 16. So if I do the same, I have A times B. I have my tensor product here with A and B, and I have K, but I already know K, so I can pre-compute everyone because I know how I decompose, and then I can do my dot product. And here you have to think about Vincent. I already know my coefficient. I already know which are the bigger one and which are the smaller one, so I do an ascending sum because it's more precise to do an ascending sum in that case. And then I get my result. So for that, we can emulate matrix multiplication. So GEM stands for General Matrix Multiply. So it includes 32, so it's single precision general matrix multiply to be precise. And here I can get, okay, I have my matrix A, my matrix B, so 4 by 4. Let's start simple. I get my matrix K with my brain float, so the decomposition of my brain float. I slice, so I use the CUDA cores to slice my matrix A to put the matrix in a matrix on brain float. I do the same for B. And of course, we need to have big matrices to compute with tensor core efficiently. I have bigger matrices like this. I perform the computation on tensor cores, and then I use again the big tensor core I showed you just before. So for example, in N100 or H100 for brain float, which are really big. And then I use a CUDA core to unslice and to do my sum to get my result. So that's really, really efficient to do this kind of stuff. So for example, here, with a simulation for weather forecasting simulation, you get the resolution here, so 25 kilometer, 2.5 kilometer resolution, and you get the several here, the several computing here. So in float 32, in brain float 16 times 9 here, And you see that sometimes, for example, here it's really clear that you get a more peaked distribution, and this is the error. And the more peaked distribution you are, the less error you have. So you are really close to zero in terms of error. Of course, because 3 branch processing gets more information than 1 float 32, of course, because we do what we can. And it's also faster, 2.4 times faster. So you get a more precise result and you are faster. Nice, quite nice. And then, of course, I told you at the beginning of the presentation, people are complaining because there is less float 34 computing power in Hopper, for example, or in Blackwell compared to Hopper, and in Rubin also compared to Blackwell. And they complain because, of course, they want to use a float 64. Let's emulate float 64 with this technique to see what's going on. So float 64, as Vincent mentioned before, it's a 52 bits of Mantissa. Okay, it's not a multiple of 8, so I can use 9, 8, so 56, 48, depending on what we want to do. So let's have matrix A and matrix B in float 64. Let's have a 56-bit Mantissa because I cannot do 52, it's not a multiple of 8. So let's pick S equals 7, so 7 coefficient per float 64. I slice my first matrix. I slice my second matrix. I use integer, so that's also a trick. You can see an integer as full Mantissa with no exponent. It's okay, totally possible. So you do your matrix multiplication with integer, which are really big compared to the other, as I mentioned before. So here you see the tensor cores for M100 and H100 for integer. And finally, you can unslice and get your result back. And you have even much bigger matrix to fill inside your tensor core, and that's really important to have big matrices. So if you want to do some float 64 computation, you can. And they did some tests on the material science simulation, so by Berkeley, here, the Chisholm simulation with 56 bits. And they get 2.1x faster than the implementation they had before. And the nice stuff with that is you can play with the precision you want because you are not stuck to a certain number of bits inside your computing. So you can say, okay, let's try with 40, 48, 56, 64, 72, depending on what you want to do. Depending of the part, if you have a big matrix, maybe some part could be computing less precision and more precision. You can do what you want. So here, of course, if the matrix are really small, you don't gain so much. If the matrix start to be a bit bigger, you start to have a slightly performance improvement. And here you really see that if you can drop a bit the precision, because it's enough for what you want to do, you can have really nice speed up. So more than 4 here in S equal 5, so 40 bits precision. But still it's 72 bits precision compared to 252. You have much more precision, but you are still faster here. But here where you have 1, so here it's a classical float 64 computation in dashed line in red, and everything is faster because tensor core are really much more efficient. Because of course, once you want to do a tensor core to compute float 64 compared to int 8, you have at least factor 8 in terms of number of bits you want to deal with, so 8 times more cells for the int computing. So of course, that's really powerful. And you can use your computing, your integer to compute everything you want. You don't have to be stuck only with float 32. You can say, okay, 52 bits, but let's try. Let's play with it. Let's understand what's matter. It opens the door. So I don't say use it right now, but play with it normally should be quite interesting for you at some point. So in terms of accuracy, so they pick 500 matrices for the sweet sparse data set. So that's classic data set. Once you want to have a new linear algebra library, you pick this data set and you say, oh, I get my QR, my eigenvalue, my whatever faster than everyone else. So you get this kind of stuff. So here you have all the precision. So black dot, you have the float 64 here. Triangle, you have the S equal width, so 64 bits. So triangle, so really close here. If you drop a bit of precision, 48 bits here, you get the orange square, and here you get the diamond, double diamond in 56 bits for SYCL 7. And of course, people are lazy, and I'm really glad they're lazy. There is an automatic mod here. So you can say, okay, figure out what precision I want this to be precise at 10 to the minus 15, for example, and do what you want. Pick the precision you want. I don't want to know. I just want this precision. Then do what you want. And they are a bit conservative, of course. There are a bit of margin compared to what you ask, to be sure that nobody will have some problem with the precision. So that's a blue dot here. So you see that it's really nicely done. So really efficient. So in terms of floating point emulation, so the current algorithm falls back on the classical DGEM in float 64 of QBLAS, for example, if the emulation is not possible. For example, if your matrices is not good, well conditioned, you cannot emulate. If your matrix is not well conditioned, if you do a computing, think about Vincent, probably the result will be false as well. But if the result is false with DGEM, it's not the fault of the emulation, because the emulation is not called. If the emulation is not called, maybe you can have a hint to say, maybe my matrix is not well conditioned. That's also a nice trick to have. So the libraries will have the emulation. So you can already do some stuff with QBLAS with environment variable. It's not really elegant, but you can do this kind of stuff to say, okay, which mode do we want? Which precision do you want? It's already possible with, I don't remember, CUDA 13.1, I think, something like that. So they will have granular emulation algorithm. You will have fine-grained control of what's going on. It's not the case yet, but you still can do a lot of stuff, in fact. And the profiling tools for precision is under development for now. They are not really ready yet, but that's ongoing. That will work at some point. So in conclusion, and then we'll have the break. Really nice in terms of timing. So if you want to do some NVCC with CUDA, NVC++ with C++17, C++20, it's okay. So we tested that since the HPC SDK 24.3, and here we will use 26.3 for the lecture. So if you have the compiler, you have all the tricks that come with the compiler. So avoid static allocation, but if you want to target specific GPU, you can use the CUDA visible devices. It's okay. It's a CUDA, so no problem with that. No explicit linking, as I said before, otherwise you will have a link, but a crash at the execution, so you don't want that. And with industrial software, of course, you see that, of course, we don't have any more K80, so Kepler is dying, and MathSQL is dying also. So keep an eye on that, of course. Depending on your architecture, be sure that you can use your GPU as well as possible. And thanks for your attention. Question on Discord or no? Everyone is happy? Okay, so everyone is happy. I don't look at the question anymore. So it's time to do a break. So coffee break for half an hour, and we will start again at 4 p.m. 1, 2, 3. Okay, we are back. The mic problems, but normally should be okay now. So yeah, we will start the hands-on session for wizardry with GPU, with Insight, and all the stuff that's come with it. So I will start a bit. So just to give you the link here. So if you want to follow, maybe I can put that in the chat. So if I do that, it's not up to date. Firefox, please. Is it up to date now? Ah, merci. Okay. Donc this one and this one. Hop. So you can follow gently. So I recommend you a lot to use Apptenor for this hands-on. If you manage to see the GPU with Podman or with Docker, is fine. So you get also the command here as well. So you can have this one for Podman. Yes. This one here as well for Docker. But we'll do a lot of interactive stuff here. So we'll use NCs to profile, Insight to visualize. So if you are only in one container, it could be quite horrible. I don't really know how to forward the X11 stuff inside with Podman and Docker. It's really simple to do with Apptenor. And I will show you everything with both Apptenor and my Insight, one of my Insight on my computer, because of course I have several. And normally should be okay. So if it's okay for you, I will start a bit the slide so you have the time to pick the image. If you want also maybe yes on must, because they had question on must. Okay, let's have another one. Sebastian is not here, but I'm pretty sure he will say this one. Yeah, should be okay. Once you jump on must, you are in your home. You already have some account. And of course, you don't want to be there. You want to jump on lab data formation. And here you pick your account. Should be Grayscott GPU normally. Yes, you have all your account here. So pick your account and not one of someone else. And here normally you can have, you have all your account and you can do everything you want. So don't pick the image yourself, not necessary. All the image are in Grayscott container already. So you get the stencil GPU job for today. So you don't have to duplicate everything. Just pick this one and you don't have to duplicate. You just put the full path on your, yeah. Okay, I can start my I can start my slides just to have a bit of time. Normally should be yeah. Oui, of course. You mean this one? The path. So yeah, if I jump here, it will be Grayscott container here. So in lab data formation, Grayscott container, you have all the containers, so CPU, GPU, everything. So I pull everything, so you don't have to do it yourself. And normally it's supposed to be updated. So yeah, 6 GB for this one. And so then you can have, normally you have everything on your account. To start a job, you have a little job example on all your accounts, so you can start a job, ask for GPU, so A100 for example, and then you can send your job and play with it. So don't forget to bind the build directory and also to bind the sources, for example, to have the sources not in the image, otherwise they will be in read-only. Or if you just want to start the profiler and play with the code itself, it's okay too. Is it okay? Yeah? Yeah. Normally, you already have an example. I can show you here in the documentation. Job submission, job script, yes. So normally you have already in your all the account, all the SSH account in lab data, as I show you. You have a job submission example. And so you have a submit file, you have a script file, and inside the script you should have something like this with the image which is not the right one. You have to put the GPU one that you want to use here. And then you bind here I bind the sources, I bind the build. You can bind everything you want depending on how you want to use the image. No, I prefer to have the build inside the home Jovian examples, but if you prefer /build as before, it's up to you. You do what you want. And then we have, so this is a script of the job. So to start the job with htcondor. So you all have that in your account, and you have another script here. And this script is run inside the container in the job. So here it's an example with an Adama product, of course, but we will not do some Adama product for this lecture, of course. We'll do some Grayscott. But that's the idea. Here you will put the command that you want to execute inside the container. So the command I will type in VS Code live. Normally. And you should get everything properly done. An Aptainer is more efficient than before, so you don't need 80 GB anymore to pick an image of 6 GB. But you will need something like 30. So still big compared to the size of the image. Yeah, okay. 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 So is it okay from my side? Joseph is asking, are we using the first performance test first? No, first performance test is for CPU lecture. So here we will dive into the GPU directory in the lecture. So I show you. So typically all this stuff here. So not everything, because of course I have too much thing to show you. So we'll do a bit of jazz and we'll say to me which one you want to play with. But we will use the GPU directory for this lecture. So everything is in the same project, so you can also see the example of last week. So let's start a bit of theory. So time for Docker, Podman, and so on to get everything right. So we'll use the Laplacian implementation, which is a bit more interesting than the classical implementation that we have for Grayscott. So the idea is we have U and V images, and so it's full HD images with a stencil 3x3. And we compute the Laplacian of U, we compute the Laplacian of V, and then we update U and V, the concentration of U and V. And we loop 32 times, and then we have the new version, the updated version of U and V images. So we have several kernels, so that's a bit interesting to have this kind of stuff. So we'll do 1,000 images, so for 40-second videos, as I showed you last week. We get this time of this size of image. So one, not 1920 and 1080, but 1922 and 1082, because we have a padding around it. So that's a big trick, because of course, once we do some CPU, we can say, okay, I want to have a really fancy stencil with shrink in the border and not. On a GPU, you don't want that, because you want to start only one kernel, one simple kernel without a lot of branching, as I said before. So use padding. So I use padding also here to be sure that, okay, I multiply with zeros, but the kernel is the same, the stencil is the same, everything is the same, so everything is efficient. So we will start with NVC++, so the automatic stuff, and we will see what's going on, and then we will apply what we learn on the CUDA part. So as I said before, we use std_par equal GPU for C++17, and we run on GPU, and we will start to do this kind of stuff. So here I have my for each my cube. Is it okay for everyone? The question should be quite okay. Okay, so if it's okay, we can start. So here I have my for each. So we get in the first example 369 microseconds per step, and the theoretical occupancy 100%. If I have a look here, so what I can do is, I don't remember if I have one running. Of course not, because I killed it. Okay, so I will start it again. Where are you? Here? Yes, here. So if I manage, or maybe it's not really interesting for you, because I already put the images at the command here. No search file or directory? Why? Oh yes, CF, of course. Come on. Okay, so I start. Yeah, but come on, you know this command by heart now. You know that I have obtainer run, NV bind, a lot of stuff, and everything is working. So normally you did that a lot of times. So here I jump, and hopefully it's working. Thank you. I don't need that. I don't need that. I don't need that. Okay. So we'll let you the command. Normally you already have the command in Discord. Can do that also. So here I'm on obtainer because it's simpler for me to make it work. If you have Podman, Docker with the right command I put in Discord, normally should work. So is it okay for you? It's running? No, it's still pulling? We are killing the network of the auditorium. It took me 3 minutes this morning, but so I think we should have a waiting music in the editing on the video. No more piano. Ouais. Apparently we have time.
Mais là, j'ai pas le VS Code. Comment je fais pour ouvrir ce VS Code?
T'as quelle image?
J'ai pris l'image qu'il y avait. Celle que tu avais montrée là, la CIF.
Ah, ça, c'est pour lancer un job.
Pour l'avoir sur le VS Code, comme on l'avait.
Okay, just for people here, how many of you wants to use a GPU? So you don't have a GPU on your laptop and you want to use a GPU on Must, for example. 1, 2, 3, 4? Only 4? Okay, we will do some magic. We'll do some magic, no problem. 4, it's okay. If okay, so let's do some magic live. What could go wrong? So if I pick this one, so I said reuse that, it will be nice. So I want that. Where are you? Here, here. Let's do some magic. Okay, this one, up, up. Okay, so here I jump like this. I do LAPP formation, or maybe this. Okay, I do Condor submit of my submit Condor, which is logical, of course. I do that, and normally in 4 minutes you all get an interactive image. Oh, it's running. Yeah, so normally 4 minutes, it will be okay for every one of you to have access. Yeah, I will show you that. So the trick is, once you have the script, or maybe I can show you here. Yes. So here you have to modify the job script here. So here you put the image, the interactive code server image I am building right now. And here, so you can bind the sources and bind the build to, if you want to extract the lecture, or maybe normally you can jump directly into it. And the trick is not here. It's just once you change the image here with the new one, the code server, interactive code server GPU I just pulled, once you send the job, you don't send the job with condor submit and your submit. You use condor submit dash interactive to your submit. So this is equivalent to a srun in Slurm if you want. And the idea is you have to pick a GPU in your submit. So maybe I can show you Condor configuration. So this one. So here I request CPUs. I have the request GPUs also, which is not here, of course. How do we do that? Or maybe I can do that. And yeah, but no one understands your language. Come on. If I do, what can I do as a trick? Maybe here, Condor submit, something like that. And I say to you, command, it's, I don't know. Flash maybe? Is it presentable? Ah, much more better. Okay. So here, yeah, how do I'm supposed to do this? Yeah, this, I don't need that. Okay. Yeah, but I didn't start yet. Are CMake in code server image? Yeah, there is CMake, there is Make, there is Ninja as well, normally if you want. I prefer to use Make, but of course, if you want to use other stuff, you can. So here, it's a CPU submit. So what you want to do is request GPU 1 to have one GPU. And the other thing you want to do is the GPU kind. And of course, I don't remember how to do that. So I will have a peek to my lecture. Where is my lecture? My lecture is here. My lecture is, I have too many lectures, this one example. And here I have a submit. Okay, submit, this one is nice. Okay. So I need to pick that normally, and I can remove this and put that here. So request GPUs equal 1. I want one GPU. Here you put the GPU name. So we have 44 and 3, 6A100 and 6A100 80 GB. So you have this one. I can add also 100 80 GB with a space, because why not? So you have to put one of them. So for example, if I do a 100 in GPU name here, you can say that. Here I put GPU name because I did a test on all the GPU available at the same time to show you the performance side I showed you before with a number of threads, this kind of stuff. Of course, here you want only one GPU. So you do that. So if you can put a 100, since you are 4, normally it should be okay. You can use C4, normally it should be okay too. And if you put your mail here, you will be notified once the job is finished. So if you disconnect, you have the confirmation that everything is okay. Here we will do the thing in interactive mode, so it's not a problem, but it's okay up to there. For the GPU, maybe it's done. Not yet. Okay. The image will be in a container as the other GPU. Come on. When you start the job, you don't worry about it. Or maybe if I can do that. Where is NC? NC team? You are lucky. Yes, that's the point to have a chat. Come on. Are you sure you want to send something back? Yes, of course. So here you get everything. So I have extra stuff. I'm pretty sure that it will be okay. And you can remove the comment if you don't want them, of course. So you can pick everything. Yeah, Michael, you're right. Sometimes you have to source, sometimes you don't have to source. I never have to source my BashRC. Vincent never has to source my BashRC. Sometimes you have, maybe it's a difference of version. That's strange stuff of Obtainer. So is it okay for the update of the submit? Yes? For this one? Yeah. What? I have an issue with Docker. But I had the issue with Podmat, so I use Obtainer, so that's logical.
So the containers is running fine, but inside of it I can't do NVDSM. It doesn't recognize the command like the NVIDIA packages aren't installed yet.
Yeah.
Even NVCC doesn't know. No,
NVCC is in OPT, so normally you have a variable. It's NVCPP in capital. If you do echo $NVCPP, normally you should have it in the container. Because sometimes you want to compile with NVCPP, sometimes you want to compile with NVCC, so I cannot do CXX as everyone because I want to change. Brace.
Oh.
Or nothing. Yeah.
Okay.
And you have the same for NVCC. You have capital NVCC to get NVCC. That's the trick I use in the container. But for NVIDIA SMI, maybe did you try to remove the DRI stuff? I use only GPU all.
I'm gonna try.
Maybe it's working only on my laptop and not other. I don't know. So maybe you can get rid of it and it's okay.
On va l'avoir directement sur le serveur interactif du coup.
No? Ah là là. Bon, c'était long. Ça arrive. So there is another trick you want to do if you want to jump on must with an interactive image. If I pick this one, is to use a remote container server. You want to forward the 8080 port from the local server where you are to your laptop. So you have to type this command, so with your user for must and with the server that you have to forward the port. And you have to let the command hang in a terminal just to make sure that the bridge is done. Otherwise, it won't work. And then you can start the job, and normally it should be okay. Yeah. Um, okay, so 1.1.5, but is it the right one? It's a good question now. Mm. A6, 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 A6. Come on. Mm. But come on. Come on. Oh, yeah. It was pulled, but not in the right directory, but now I should have it. Of course. Il est là. This one. Maybe you should put that. You have points, it's okay. And see. That. Should have that in your in the script obtainer run. You should have this path. It's asking, hi, what can we do meanwhile when you have to pull the image? Which one can we try to build? Okay, so yeah, I will answer that. So for the other who have something working, we will start that. So then we can have a look and do it after that. So I have my server running since I don't remember when. So here, if I give you that, so we are. So it depends if you are in Aptainer or not. So I will give you the two commands, maybe everything. We will do everything here in Discord, so you can start. So if I do this kind of stuff. So depending if you are in Podman, in Aptainer, it's not exactly the same CMake command because if the thing were compatible, it will be a dream. So the idea here, if I jump in Aptainer here, I will activate NVCPP first. So we will spy a bit what NVCPP is doing to paste here. Command, yeah, build, cd build, of course, yeah, better. Thank you. So here I have my NVC++, and then here I can compile everyone. So I have 24 core. You can compile as you want. I should be okay. Come on. Yes, yes. Okay, the end is a bit slow because NVC++ is a bit to try to optimize a lot, so it's a bit slower. Okay. So here I compile everything. Oh. Yeah, it should be okay normally here. And here we'll ask NSYS to profile the first example here we have for the Laplacian with a small example, so still HD example, but with only 100 images because we just don't want to be too long, just to see what's going on. So here I go here, I do that. You have everything in Discord if you want to follow. But it will be really quick normally. So. Okay. So now I ask NSYS to profile with an output because it's better to have an output. Otherwise, you have a weird naming and you never remember which is which. So you ask to get the NVC Laplacian. So I told you about the Laplacian. So I have I compute U, I compute V, then I compute the updating of the concentration, and it's okay. So here I have a report, and I will pick the report. Where am I? A good question. Here? No, not you. Not you. I have too much tab. This one? No. So not you. U. Okay. So here I have my CIF, my build, and here normally I get my report here. So normally it should be quite okay for everyone. So here I have a report, and I want to open the report in Insight to see what's going on. So basically, what can I can do that. I mean must, so of course I don't want to be there. Change nothing. So, or if you have only one Insight, you can start it. So I have several, so I need to use a command line to start the one I want, of course. But this is because I have several HPCSDK on my laptop. So here, Control O, I open my report. Here. So is it clear in Discord? Is it okay for you? Should be okay with the HPCSDK 25.3 normally. Okay. Okay, Céline is happy. So normally, if you start your Insight, so not a two-hold Insight, but it should be quite okay. So here I have the 26.1.1. I do the performance test with the 26.3, don't remember what, 3 something. It's compatible for what we want to do, so no problem. And here we get the CPU activity, the GPU activity with the context, with the memory, the unified memory I told you about just before. Give me some room, please, now. Thank you. I cannot. I try, but I cannot. I can hear in this widget. I cannot in here. I cannot hear. That's strange. As Sébastien said, it's not visual in a browser, so you cannot zoom everything you want. I'm pretty sure on the stream should be okay, but yeah, it's a bit small here. But yeah, the thing I want to show you is this. So if you select a bit and you Shift Z, you zoom. And here you see that my first 2 calls of a kernel are really slow compared to the other one. For a simple reason, here I have a lot of memory transfer. And each time, maybe I can zoom also here to show you. Here I have my speculative prefetch. I have a page fault, and of course it takes time. And it takes a lot of time. So if I, please, thank you. If I resume a bit, for example, here. So here I have a really long kernel, and here 3 really small. So it's the same kernel. So here I compute which one here? Compute V. Yeah, so here I want to show you that also. It's important. Give me some room, please. So here I have all my kernel calls, and here I can zoom. At least this morning I was able to zoom. Please. Okay. So here you see the strategy of NVC++. So I get the beginning and the end of this particular block. So this is the first one. So then I can move to the second one, to the third one, etc. So you see that here I'm at 5 milliseconds to run one kernel. Here 3 milliseconds, and then it's okay. It's 189 microseconds, which is much better. And then we can move on to the next part. So I compute U, I compute V, I upgrade the concentration, and so on and so forth. Like, yeah, but that's the problem of non-browser interface. But okay, here should be okay. I cannot zoom on the I can zoom in the timeline, but I cannot zoom the interface itself. It's only possible here. I don't know why, but for the other I cannot. Devs of Insight, please, if you know how to do that, send me a mail for next year. So here you see the time you spend on the kernel. And the interesting stuff to do some wizardry, especially if you want to do some CUDA after, is the size of a grid and the size of a block determined by NVC++. So determined by thrust under the hood. And here you see an interesting strategy. The block is 1 dimension, even if we have a 2-dimension computation. And it's 256. If you look, maybe not today, of course, but on Wednesday, once you will have the lecture with NV Fortran, you will see that NV Fortran does not have the same strategy. Here it's 256, and NV Fortran is 128. And they have better performances. So you have different strategies. So it's a nice strategy, in fact, here to get some performances. The good news here, theoretical occupancy, 100%. So I did my job well. I have a nice program to fit in my GPU. I don't have any holes or any problem of fit here. So it's really nice. I have also the latency to start the kernel. So you see the kernel here. Maybe if I zoom here, they don't touch each other because you have a latency to resume to start the kernel again, etc., etc. So you get the latency here also to have the information. And you get also the stream. So the default stream is the 7th. So if you use several stream, of course, you will see all the streams. So here there is only one. That's the first example. Really simple. But that's interesting to see what's going on here. So is it okay? Okay. Seems to be okay here. Okay. There is a documentation issue here. Yeah. Okay. So is it clear up to there? Yeah. Okay. So we can continue. So here, 300 microseconds per step, and we have a theoretical occupancy of 100%, which is nice. So we want to have row-wise or column-wise. That's a good question. So if you have a grid, or maybe I can go really quickly with that. So if you have a grid of 36 by 60 and block 30 by 32, you will get performances with 975 microseconds per kernel for the total call. Once you do CUDA, the contiguous axis is the x-axis. So I want my multiple of 32 to be in the x-axis. And if I put my multiple of 32 on the x-axis, like this, I get 361 microseconds for one kernel. So more than a speedup of 2, just because I swapped my axis. So that's really costly. So you cannot do that with vectorization because the compiler will say, no, no way, you don't have contiguous data. Since you are in a kernel, remember every time you are in a kernel, you can do everything you want. If you do an extension table to pick data everywhere, you can, but you will kill your performances. So always use a contiguous axis well. So that's why in Insight here, we see that here, the contiguous axis 256, they use a contiguous axis. They don't bother with the X and Y axis here, not necessary for, and it's really much more simple to do this kind of stuff with one dimension, in fact. So that's a very nice trick. That's also a nice trick to have a 2-dimension here because, of course, it's much simpler to compute the index because you have an index in X and an index in Y. So to work on a matrix, it's much more simpler, but the compiler doesn't see that. So here, if I'm column-wise, so I have a block column-wise, so my warp is on x-axis, as I said. So 361 microseconds, much better than before. More than a factor of 2, it's important to have in mind. So we can split our problem like this. So 32 thread, multiple of 32, of course, 60 block for 1920, and here 36 block with a 1080, 1082, because we have a padding. As I said before, we want to have the same kernel everywhere. That's much more simple. So we do that basically in the lecture to be sure that everything is efficient. So from NVC++, it was okay. Maybe we'll do that together. It's better to do that together. So maybe I can let it open. So we'll continue here. Yes, here. So maybe I can do that. And I can do that. Yeah. So if I do this, you have the rest. So 4 podman or 4 obtainer. So what we will do here is we will kill. Where are you? Here. We'll kill our build directory because star. Okay, star. We'll kill our build directory. We will recompile to enable here. So enable CUDA. So here I compile no NVCPP and CUDA. So yes for CUDA. And normally it should be. So here, yeah, that's the old way to do some CUDA. I will show you the new way on Wednesday. Yeah, here we will not have time for that. And here, so I compile. Come on, come on. Come on, come on. Okay. So here I compile everything but for CUDA, so I don't have the same. So you get Grayscott's CUDA, of course, here. So hopefully everyone is following nicely. Yes. CUDA toolkit matching the current driver version. Ah, yes. If your CUDA toolkit is not installed with the HPC SDK, I use only the HPC SDK, so I don't know. That's the problem. Maybe with the CUDA toolkit, but if you get the right version of the CUDA toolkit, should be okay. But I really prefer to use the HPC SDK, so I don't really know. Maybe you have to check with the site here. Should should be okay. So now we will do some check with the Laplacian here. So you can have everything. And if I jump here, we can start to profile the Laplacian in CUDA to see what's going on. And to see, of course, if Insight is happy. Strange. What are you doing here? Yeah. Oh, yeah, maybe it's. Oui. Inside the container? I don't have. At least you can CUDA toolkit. The path to the CUDA toolkit is, it's a good question, I don't remember. But I can figure out here. So it's OPT, NVIDIA, HPC SDK, Linux 26, CUDA with some version, I believe. 13.1 normally. Yeah, should be this one. If you want the CUDA toolkit, can put it in Annecy. Where is Annecy? Annecy. Here. Should be something like that. But normally it's automatic because you have the NVC. NVC compiler, and normally NVCC is supposed to figure out everything automatically. Okay, so if I show you that, that's a good illustration of what I said before. Here you see maximum dimension for the block and for the grid. So I cannot have more than 1024 threads on X, 1024 on Y, and 64 on Z. And in total, in one block, I cannot have more than 1024 threads for whatever dimension you want. So if you put too much, you will get an error. That's why you have to multiply the number of blocks instead of trying to have a very dense block with a lot of threads. And you have a maximum of threads per multiprocessor also. So you don't want to, you want to have some flexibility to have enough block in enough warp in flight at the same time, but not too much. Otherwise, the GPU will complain. So it's a difficult balance to have enough, but not too much. So you really have to play with it. And see, yeah, here you have also
on my laptop, on my laptop, on my GPU. Here, 2 copy engines, so I can copy in both directions at the same time. That's a feature we can have since a while in a GPU of NVIDIA. Or you copy really twice faster in one direction on one other, but you can do both at the same time. So you can have a stream to fill your GPU, a stream to get the result back, and a stream to send computing, for example. To do 3 stuff at the same time is possible with this kind of configuration. But of course, you have to check. And so here, yes, of course, I have a report. I have to do something with my report. So my report is where? Is here because I didn't put no, it's not this one. Come on, come on. Okay. Okay, so I have this one. So I want to pick my report. I forget to put a -O, but not a problem. I will pick this one. I go here. I say that. That's okay. So here can have. We don't care about the CPU. Oh yeah. Oh yeah, there is no SRC here. It's this one. The copy paste is wrong. This one. Good point. Really good point. So here I have all my kernels. I have my memory. I can start here to zoom a bit to see what's going on. I need to zoom a bit more. Okay, so here you see I compute my Laplacian for one PC, so I get all the information. So here I cannot zoom, of course. I have to select to zoom. So if I do that, key my interface like this. So here I have concentration of U, concentration of V, and concentration of U, concentration of V, because it's the same kernel. Here it's another kernel, so I have to do that. Okay, and here I have, so here you see the strategy, the 60, 125 and 32.8. So the strategy we get here. And we get also an occupancy of 100%, so the strategy is working. Not exactly the same as the one of NVC++, but it's working. So if normally if Annecy told you 100%, it's okay. You don't have some problem with that. That's a question. No question. Okay, nice. And I was telling that. So here we get 62. I didn't run the. You get the final result before I mess up my command line. Laplacian transpose. Anyway, we are a bit late, so yeah. So 61 microsecond, occupancy 62%. If you transpose, so you do the wrong stuff, so you transpose and you can have some problem with that. NVC++, 256 strategy, occupancy 100%. So yeah, I skipped this one, but you can find it's not as efficient as the other. It's maybe not a problem to get that, but of course, having one dimension is annoying, even if the compiler can do that. So we can say, okay, 135.60 and 832. So 536 microseconds, and we do the same, but we swap everything, and here we get the best performances. And normally we should have this. Where am I? Here? No. Here? Yes. Here, 164 microseconds, so a bit better than last year. But you see that here, I can improve the occupancy by checking the boundaries here, the number of block, number of thread in block, and the number of block in a grid. I can inspire from NVC++ to improve that. Then I can improve my occupancy, and then I can transpose to have a better occupancy, because the problem is if you are not efficient and you occupy a lot of GPU, the inside see nothing. So you need to say, okay, if you have 100% occupancy, it's nice, but maybe you can improve for roughly a factor of 2 if you transpose. So if you use the x-axis as a contiguous axis. So always criticize the output of a profiler, because the profiler should tell you that it's okay, but maybe something is missing still. Or maybe I will do that. Yeah, we can do it. We are not late already. We are large. We are large. It's okay on Discord, okay. So we can do some streams. So the idea is to say, okay, I compute the Laplacian of U, I compute the Laplacian of V, I update the U and V species. Maybe could compute Laplacian of U and V at the same time. Could be nice. Of course, if I have 100% occupancy, it will be difficult, but let's try to do it. So if I do that, I need to have less than 50% occupancy. Remember, that's a parallelism by opportunity. So if I have 100%, no way I can do the same both at the same time. So we have to figure out how to change. If I'm above 50%, of course, I will have to wait for the other to be executed. So that's also a trade-off, and that's why the problem is once you use stream, you cannot improvise. You cannot say, okay, I have my kernel tuned for a single stream, I will use it on several streams. You will just have several streams, but with the same performances, even a bit worse, because you have to tune your kernel to work in team with others. That's otherwise you will not have performances, of course, because you don't have the space on the GPU to run the kernel. So we can improve a bit computing and data transfer. So here we are doing classic stuff. So we compute and then we transfer, and we compute and we transfer again. Of course, that's a pity. You want to do both at the same time. So if you do all the computing and the transfer at the end, it's the same problem. So what you want to do is to do this kind of stuff. You overlap, so you compute and then you retrieve your result and you start another kernel and you compute since the results are also moving. So you need to have a buffer to do that, but you can do this kind of stuff. If you don't have enough computing, that's our case compared to the transfer. We are stuck at some point because, of course, we cannot have two two compute running at the same time, or two transfer running at the same time, at least on this kind of card. So this, you are IO bound, so you can not do much. You have to play with it again. So if you have to do some asynchronism with NVC++, we'll see that right now, because it's not the same coloring. So since it's not the same coloring, purple means you do some transfer from with the pin memory, and the light green is the same. So if you don't have the color as before, so I have to zoom. Yeah. If you don't have the green and the flashy green and the flashy red, that's not pin. You call the CUDA malloc, classic CUDA malloc. If you hear the CUDA malloc host, here you call the CUDA malloc host, and then you pin the memory, and then the transfer is much faster, and you can overlap transfer and computing. That you cannot if you don't do this kind of stuff. Maybe I have. Yeah, here's an example, a really small example, of course, with an Adama product. So here you see I have several streams, so 4 streams, even more. You have more streams? Okay, I did a lot of streams here, just for the fun of it. So you have a big array, for example, to compute, and you split your array into streams, to chunk, and you have 1 stream per array. And here you can finish to compute some array while another is doing some transfer already. So if you have problem of latency of transfer, this kind of stuff, you can do this kind of trick, but you need to get this coloring, so to use CUDA malloc host on the host and not classic malloc, to have pin memory to be sure that the parallelism will work. Otherwise, you don't get parallelism. Is it... Joseph get an implementation in Roxy. Seem to work on my GPU. Okay, fine. Good point. Catastrophic error. Bare metal, yeah, bare metal, I don't feel... If you have the same environment, bare metal should be okay, but if you don't get exactly the same version, sometimes you can have some trouble. So, okay, we are not late yet. So, yeah, don't forget, as I mentioned, once you want to use some streams, use a CUDA malloc host and the CUDA free host. So you will have pin memory, and you will be able to use a CUDA mem copy async, the kernel with a grid and block that you already know, but you can have shared memory and the stream to precise the stream on which you want to start your kernel. So we can, yeah, maybe just theoretically, all the examples are already in the source. So if you want to play with it a bit later, it's okay. So I try to make a CUDA graph with a Laplacian. That's a nightmare, let's be honest, but it works, so I'm proud of it. So I get my UV images. I do a graph, so to have the Laplacian UNV compute at the same time. Of course, if there is only one kernel, not really nice. With a loop on 32. So I have several versions, one with the loop outside of the kernel, one in the loop inside the graph itself. So you can play with both if you want. And then I get all my images. So I have the other way. So with the while, so I loop inside the GPU and then I return only if I finish the graph. So you can have also this, this thing. If you have some question, I have the source code. We can comment on it if you want. So in conclusion, and we'll get some room for the question. So don't forget, once you do some CUDA, some thrust, some insight, to check, am I in the right ordering? What is the block size? Do I use contiguous axis, so the x-axis? Which number of warp do you have in flight on my GPU? So for Hopper, it's 64, it's a lot. For Ampere, it's a bit less, but you still have to start a lot of thread to be efficient. Then the shape of the block. If you transpose, sometime you get a factor 2. It's important to have in mind. The size, the occupation, the number of threads, the system time also. I didn't mention that because, of course, I forget, but calling a kernel takes time. You have a system call here. I could have a lot of your time. If you do a time with a program time, you will have the user time and the system time. And if you use something handcraft with a CUDA, for example, you will see that the time spent in the system is much higher than if you let NVC++ do the job for you. So you can have also, you can have the same computing time, but way more time spent in the system than in another one. So if you are stuck, that's also a good point to have. So you have to start enough thread, but not too many. So you have lots of limitation, as I mentioned before. So check as much as you have. And for asynchronism, it's okay, but use CUDA malloc host and CUDA free host and not the other. Otherwise, you will not be able to overlap the data transfer and the computing. Thanks for your attention. If you have some question, or if you want to play with other stuff, or if you want to ask what is the implementation for the graph or whatever, it's okay. So I have a full story here, but I don't want to be too late, so you can do that later. Maybe I can send you everything. Maybe I can send you everything. Yeah. Yeah.
Just profile the computing, or can it also help us provide like the memory and other stuff?
Ah, yeah. Good. Yeah, good question. So we can profile the computing in Insight, but of course you can also have. So it's not a profiling as precise as we'll have with Malt or with stuff like this, but you can see. So here, so I can have my kernel, I can have my memory, so I can see, okay, what I'm doing in my memory. Okay, give me some room, please. Come on. Okay. So here you have the same information. So I spend a lot of time on the kernel, but yeah, you can see, okay, I do device to host memcopy, takes this amount of byte in the copy. What is my throughput? What is the latency of the copy? What is the number of time spent on the copy? So you have a lot of information on the memory itself. So this is not the last Insight, but of course you have, so I don't have it, but you have NVTX also. So if you want to add some decorator in your code to have, okay, here I don't want to be bothered with all the kernel I want. I just want to say, okay, I am doing this stuff. You can. You can do in Python, you can do in C++, you can do in Rust, and you can do in Fortran as well. So yeah, you have much more information here. From the last GTC, there is also another stuff that will come into Insight in the future, maybe next year. It will be the the profiling on 1,000 nodes. So if you have multi-nodes, so you have a heat map on the node and you can do some stuff. Yeah.
Can you see the cache usage as well?
Not in Insight, or maybe there is a trick that I don't know. Generates the high level.
Because you can see the prefetch, right? But
you get the speculative prefetch.
so what is the what is this prefetch for? Is it for the cache or is it for from
the speculative prefetch? Do I have one? Yeah, no. Okay, I will pick. Now here it's I need to have okay, this one. Yeah, nice. So here the speculative prefetch is once you use NVCC or thrust, for example, and you don't do the transfer explicitly from the device to the host or from the host to the device. The driver will figure out that there is a problem and do the transfer for you. So it's just a transfer between the host and the device. You don't have the details or where is the memory inside which cache, inside the shared memory, inside the L2, the L0, the L1, this kind of stuff. You don't have that. You just have, okay, here there is a page fault. I did the transfer for you. That's it. You don't have much more information. At least for now, there is no much information.
Do you know if there's any tools to obtain the usage of the cache?
The insight inside the cache?
Yeah. Well, how if the memory, of course, I can always benchmark and so on, but it's nice to have a.
Yeah, but if you bench, of course, you can guess. I'm not sure if there is some tools for that. Or maybe with CUDA GDB, it's possible to do some stuff. But with Insight, I'm not sure. I never tried, in fact. But I don't have much information. I have the std par here, but it's really high level, just to tell me, okay, you use a for each. Could be interesting. You have a for each somewhere. You know it's a for each and not a transform or stuff like this. Or maybe in the CUDA API, if I unzoom, do I have some stuff? No. Or maybe, do I have? No, of course, I don't have. You can see also the graph inside Insight, but in terms of really caches, I don't know.
Okay, so one final question. Of course, on CPUs, unrolling is very, or can be in cases, crucial for performance. But due to out-of-order execution, of course, we don't necessarily need to unroll as much as perhaps on a GPU where you don't have out-of-order execution. Do you know how much performance you gain if you unroll loops, GPUs?
So you have a loop inside your kernel and you want to unroll it, because here we don't have loop. So we let the GPU does the loop for us, in fact. If you unroll, that's a tough question. We have to do the check. On CPU, NVC++ is really aggressive on the optimization. On GPU, I never try to check. In fact, I need to check the PTX to be sure that if the GPU say, okay, maybe I will unroll, or NVC++ or NVCC will unroll. I don't know. We have to check. For Grayscott, I'm not sure it's it's something to do, but or if you have really big image, but for the part, or maybe if you hardcode the boundaries, the compiler could figure out. Since maybe one thing, NVC++, NVCC are both based on LLVM. So normally, if LLVM thinks that it's a thing to do, normally you could do this kind of stuff also. even if they disagree on what optimization to do. For example, if there is an undefined behavior, NVC++ or NVCC will optimize a lot because it's undefined. So if it's undefined, I can do what I want as a compiler, and the other will not. That's why there is a lot of call in integer once you have a loop, as I said last week. But otherwise, yeah, we have to check. That's a good question. We have to check. So maybe if you want to have a look, if I show you that, we not want to do that, but here normally I should have a graph here. So I try to do, if I get some room here. So here, so I put everything in the graph. So the transfer, so here I have a little function to create a node, so create CUDA kernel node. So just I wrapped the function to create a node because you have to fill a structure and pass the structure to the CUDA graph at node. So you have several now. Back in the day, there was only one. Now we have several, so you have to pick what you want. We have an extra argument here, which was not there before. So if you have an old CUDA, maybe it does not compile because this is new with CUDA 13. So if you have a CUDA 12, maybe you cannot compile here. So I put everything here, and here I can create. So here I create my graph. So once you factorize everything, it's readable, roughly readable with 3 kernels only. But here you say, okay, I have my vector of nodes. I create my nodes. I pass my parameter. So you can pass parameter, you can pass kernel. So here normally it's a kernel. If I jump Laplacian U here, so I have a void star here, Laplacian U. So I define. So this is prototype. So I pass a prototype here, I put the prototype here. So it's really C related, in fact. So it's not a lambda, at least not yet. Maybe it will come at some point. You do the same for V. You do the same for the concentration. And then you can also print a dot to have the graph of your kernel. That's really nice to debug. So you have all the information of your kernel, which data, which one. It's not really, there is no much color in it, but you get nice information.
Okay, so perhaps one final question.
Yeah.
So you on your website you write a description for the lecture. So at 2 you had shared memory, global memory.
Yeah.
Did you go over shared memory?
On this one, I let I didn't. I'm not sure. I tried to use the shared memory here.
So my
but
question
here,
is,
yeah. Oh, maybe yeah. I forgot to mention, but yeah, here I did not use the shared memory, but I have. If it's the right version, because of course I have a lot of versions of my. Yeah, I have a pyramid version of the Grayscott, because of course we'll do a pyramid version of the Grayscott. And here normally, so here I have my kernel, but I'm not sure I'm using, no, I don't use yet shared memory here in this version. That's really difficult to make it work, but I do my pyramid on my GPU, so a lot of pyramids. So I have a meta image with a lot of pyramid, and I stream the pyramid, and that's really, really efficient.
but my question is,
yeah, I don't have a shared memory yet.
okay, but what is your experience with not only shared memory, but constant memory? Because I think, if I recall correctly, shared memory, I mean, pollutes, I believe, L1, but constant memory is a distinct part of the memoy bus, I believe.
Oh yeah, it's a good point. Maybe we can put the the weight of the stencil in the constant memory. I never tried. I have to try. Good point for next year. Really good point. Question on Discord? No, it's okay on Discord. So of course you can play with all the examples. There are much more examples that could fit in 2 hours, of course. So if you are curious, if you want to do some device, some asynchronism, some location, some graph with while, because yeah. So here, yeah, that's quite hard to do. You have to make a nice design, use a whiteboard or a blackboard to be sure that you understand what you are doing if you do some graph, but and then you have to tune your kernel to start nicely and not overlapped on the GPU, otherwise you kill the parallelism. But open doors, so always nice to open doors. So if you don't have more questions, yeah, seems to be okay. Yeah, so I think we are not on time, but practically. So thank you everyone for attending this day. We did a lot of magic on GPU. So tomorrow we'll do some Python on GPU. With a lot of technology. So thank you all for attending this day. Thank you all the satellite sites for participating to the Grace Code. Thank you also Carlos for the nice presentation of this afternoon, and see you tomorrow. Bye.